the Sun is part of a wider cosmic environment. Its wind presses against the interstellar medium, cosmic rays sweep through, and galactic magnetic fields tug on its outskirts. Placing our star within this context broadens our understanding and connects solar physics to galactic dynamics and interstellar weather. The solar wind is a continuous stream of charged particles flowing outward from the corona. Near Earth, it travels at speeds of 400 to 800 kilometers per second. The slow wind emerges from regions with closed field lines, while the fast wind comes from coronal holes where field lines open to space. As the wind propagates, it carries the magnetic field, shaping a heliosphere that envelops the solar system. At the outer edge, called the termination shock, the wind slows abruptly when it encounters interstellar material. Beyond lies the heliopause, where the pressure of the solar wind balances the interstellar medium. The structure and variability of the solar wind influence space weather and cosmic ray modulation. Galactic cosmic rays, high-energy particles from outside the solar system, constantly bombard Earth. The solar wind and magnetic field act as a shield, deflecting and decelerating many of these particles. During solar maximum, when the magnetic field is strong and turbulent, fewer cosmic rays reach Earth. During solar minimum, more cosmic rays penetrate the inner solar system. This modulation leaves traces in cosmogenic isotopes, like carbon-14 and beryllium-10, which scientists use to reconstruct past solar activity. Cosmic rays also play a role in atmospheric chemistry and cloud formation, though the extent of this influence remains debated. Understanding cosmic ray modulation is part of understanding the Sun's broader environmental impact. Earth's magnetosphere is shaped by the interaction between the solar wind and the planetary magnetic field. At the day side, the magnetopause forms a boundary where the pressures balance. On the night side, the magnetotail stretches thousands of Earth radii. Reconnection in the tail releases energy that powers auroras and substorms. When a CME, or high-speed stream, hits the magnetosphere, it compresses the magnetopause and injects energy. Charged particles spiral along magnetic field lines and precipitate into the polar regions, exciting atmospheric atoms and producing shimmering curtains of light. The colors of the aurora depend on the type of atom and altitude, creating green oxygen glows and red or purple hues. Observing these lights connects us to the dynamic space environment. Our dependence on technology means we are more vulnerable to solar storms than in the past. Satellites rely on solar panels, which degrade under constant bombardment by particles. Electronics can suffer single-event upsets when struck by energetic ions. Communication systems that rely on the ionosphere, such as high-frequency radio and GPS signals, can experience outages during flares. The aviation industry monitors space weather because increased radiation at high altitudes can expose passengers and crew to elevated doses, especially on polar routes. Modern society's reliance on precision timing, navigation, and power distribution requires planning for worst-case scenarios. Investment in space weather research and mitigation strategies is an investment in resilience. A new generation of missions is poised to deepen our understanding of the Sun. Solar Orbiter, launched by the European Space Agency and NASA, carries instruments that measure the magnetic field and plasma properties while imaging the Sun from close proximity and high latitudes. Its unique orbit will reveal the polar regions in detail. The Daniel K. Inouye Solar Telescope in Hawaii, with its 4-meter mirror and adaptive optics, provides unprecedented views of the photosphere and chromosphere, resolving structures only a few tens of kilometers across. Together with missions like the Parker Solar Probe and upcoming Punch CubeSats, these observatories will offer complementary perspectives. Coordinated campaigns will enable multi-scale observations that link processes across the solar atmosphere. Throughout history, the sun has inspired myths, calendars, and rituals. Ancient cultures recognized its importance and tracked its movements to mark seasons and agricultural cycles. Eclipses were both feared and celebrated. The discovery of sunspots in the early 17th century challenged the notion of heavenly perfection. Later, the observation of solar flares in the mid-19th century revealed that the sun could change rapidly. Each generation has deepened our understanding through improved tools, from Galileo's telescope to modern satellites. Yet the sun remains a symbol of life and mystery. We still look to it for light and warmth, and we still marvel at its storms. This blend of scientific progress and enduring wonder enriches the story we tell. We begin our journey with a gentle introduction to the star at the center of our solar system, a luminous sphere of plasma that is both familiar and mysterious. When we speak of the sun, we often picture a static disk rising in the east and setting in the west. Yet this perception hides a world of motion and change. The sun is a ball of seething energy that never truly sleeps. It pulses, rotates, and breathes through convective currents and magnetic undulations. Its energy springs from nuclear fusion deep within its core, a furnace where hydrogen nuclei collide to form helium, releasing energy that migrates outward. This process has continued for billions of years and will endure for billions more. The very light that warms our planet is born in a dance of particles under immense pressure and temperature. Even though the sun appears solid to our eyes, it is composed entirely of gas and plasma. Beneath the calm surface lies a layered structure, each region defined by the way energy moves. At the center, the core occupies roughly a quarter of the sun's radius, and here the temperature exceeds 15 million degrees Celsius. In this inferno, hydrogen atoms are forced close enough to overcome their natural repulsion and merge into helium. The resulting fusion releases vast amounts of energy, including neutrinos that pass through matter with ease, and photons that begin an arduous journey outward. This inner engine sets the pace for everything that happens above. The photons produced by fusion in the core do not travel straight to the surface. Instead, they embark on an epic diffusion through the radiative zone, a region extending from roughly a quarter of the solar radius to about 70%. Here, the matter is so dense that light cannot pass freely. Photons are repeatedly absorbed and re-emitted by ions, wandering like travelers through a fog. Although each photon travels at the speed of light between collisions, the sheer number of interactions causes them to take an extraordinarily long time to reach the outer layers. It is estimated that a single photon can take hundreds of thousands to over 1 million years to escape from the radiative zone. This slow diffusion smooths out fluctuations in the core and helps maintain the sun's stability over long timescales. Above the radiative zone lies a thin but critical transition layer known as the tachocline. In this region, the rotational speed and the character of the flows change dramatically. The radiative interior rotates almost as a solid body, while the outer convective envelope rotates differentially, spinning faster at the equator than at the poles. This variation in rotation speed causes the magnetic field lines anchored in the plasma to stretch and twist. It is thought that the tachocline plays a key role in amplifying and organizing the sun's global magnetic field by acting as a dynamo. The change in chemical composition and shear flows across this boundary, generate and strengthen magnetic fields. Understanding this interface remains one of the great challenges of solar physics. Beyond the tachocline, the plasma becomes more opaque, and radiation is no longer an efficient way to transport energy. The outer 30% of the sun's radius is the convection zone, and it is here that energy moves through boiling motions. When the temperature gradient becomes steep enough, a parcel of plasma will become buoyant and rise, carrying heat toward the surface. As it approaches the top of the convection zone, it cools and sinks back down to be reheated and rise again. These convective motions are visible on the surface as a granulated pattern. At the base of the convection zone, temperatures remain around 2 million degrees Celsius, cooling to about 5,700 Kelvin at the surface. The region is a continuous churn of matter, with cells of hot plasma rising and cooler plasma descending in an unending cycle. The surface that we see with our eyes and telescopes is called the photosphere. It is not a solid surface, but a thin layer, roughly a few hundred kilometers thick, marking the depth from which photons can escape into space without further scattering. It is the boundary between the opaque interior and the transparent outer atmosphere. The photosphere glows with a golden light, its temperature around 5,700 Kelvin, and displays a mottled pattern of bright and dark patches. The bright regions correspond to the centers of convective cells where hot plasma rises, while the dark lanes mark cooler material sinking back into the depths. The pattern is known as granulation, and each granule is about 1,000 kilometers across and lasts for around 20 minutes. New granules continually emerge, pushing older ones aside, giving the surface a restless, boiling appearance. On a quiet day, the photosphere resembles a serene landscape of clouds, but upon closer inspection, it reveals the sun's dynamic nature. When viewed through telescopes tuned to specific wavelengths, the surface shows granules shimmering like cells in living tissue. Within some of the dark lanes, supersonic flows can reach speeds of more than 7 kilometers per second, producing sonic booms and acoustic waves that ripple across the surface. Above the granules are much larger structures called supergranules, roughly 35,000 kilometers across, which circulate more slowly and last for days. These cellular patterns carry magnetic fields to the edges of cells, shaping the distribution of magnetic features in the outer atmosphere. The sun's visible face is punctuated by dark blemishes known as sunspots. These are not static spots, but regions where magnetic fields protrude through the photosphere, inhibiting convection and reducing the temperature relative to the surrounding surface. Sunspots have magnetic field strengths thousands of times greater than Earth's and show a complex structure with a dark central umbra surrounded by a lighter penumbra. In the umbra, temperatures can fall to about 3,700 Kelvin compared to the photosphere's 5,700 Kelvin. Sunspots often appear in pairs or groups with opposing magnetic polarities and can last from days to weeks. They are windows into the sun's magnetic machinery and often serve as the sites of the most energetic solar events. Between the sunspots, smaller magnetic concentrations called faculae brighten the photosphere. Faculae are often easier to see near the edge of the solar disk, where the line of sight skims across the surface. Unlike sunspots, they make the sun appear slightly brighter, and during periods of high activity, they more than compensate for the darkening caused by sunspots. The interplay between dark sunspots and bright faculae subtly alters the sun's total brightness, but these variations are small, only about 0.1% over an 11-year cycle. It is the magnetic activity associated with these features, rather than the slight changes in luminosity, that has the greatest impact on space weather and the near-Earth environment. As we move outward from the photosphere, we encounter the chromosphere and the corona, layers that can only be seen in certain wavelengths or during a total eclipse. The chromosphere is a tenuous layer, a few thousand kilometers thick, glowing pinkish red in hydrogen alpha light. Above it, the corona extends millions of kilometers into space, shining in extreme ultraviolet and X-rays. These outer layers are much hotter than the photosphere, with temperatures climbing to millions of degrees. They are dominated by magnetic fields that guide the motion of charged particles. Prominences and filaments suspended above the surface trace out loops of magnetic field lines. They glow when viewed in ultraviolet wavelengths and reveal the invisible skeleton that shapes the corona. Although the corona is faint compared to the photosphere, it plays a central role in solar eruptions. When discussing the sun's heartbeat, we must consider its magnetic field, a self-sustaining dynamo generated by the motion of conductive plasma. The exact mechanism is still a topic of active research, but it is widely believed that differential rotation and convection stretch, twist, and fold magnetic field lines. The tachocline may anchor these processes, but recent studies suggest that shallower layers near the surface may also contribute. Simulations indicate that instabilities in the upper 5 to 10% of the convection zone could organize magnetic fields into patterns resembling observed sunspots. The dynamic interplay between rotation, convection, and magnetic fields gives rise to loops and arcs that emerge on the surface, tangle in the atmosphere, and sometimes snap, releasing energy as flares. Magnetic fields on the sun are never tidy. They twist and shear because different parts of the sun rotate at different speeds. The equator completes a rotation in about 25 days, while the poles take more than 30 days. The difference stretches field lines into spirals. When two regions of opposite polarity come close, their magnetic fields can reconnect. Magnetic reconnection is a process where field lines break and rejoin in a new configuration, releasing stored magnetic energy into heating and accelerating particles. Observations from the Inouye Solar Telescope have captured microflares, small solar explosions only hundreds of kilometers across, triggered when opposite magnetic fields reconnected in the lower atmosphere. These events produce sudden heating and plasma flows exceeding 20 kilometers per second. Although microflares are tiny compared to major flares, they reveal the same physics operating at different scales. The sun's magnetic field drapes and threads through the photosphere in a constantly changing pattern. Regions of concentrated magnetic field appear as sunspots, faculae, and network fields. Over days and weeks, active regions evolve, merge, and decay. When large amounts of magnetic energy build up, the field lines can become sheared. Instead of arching smoothly from a positive to a negative region, they lie almost parallel to the boundary, storing tension like a coiled spring. Solar physicists have found that flaring activity is closely associated with such sheared fields. The Marshall Space Flight Center's vector magnetograph and co-aligned H-alpha images show that when tick marks representing the magnetic field direction align along the neutral line, magnetic shear is high, and large flares become more likely. Predicting when a particular configuration will erupt remains challenging, but recognizing magnetic shear is a key ingredient. When the field lines finally snap and reconnect, the energy is released as a solar flare. Flares are tremendous explosions on the surface of the sun, heating plasma to tens of millions of degrees in just a few minutes, and releasing as much energy as 1 billion megatons of TNT. They emit radiation across the electromagnetic spectrum, from radio waves to gamma rays. The largest flares are classified as X-class, followed by M-class and C-class. This classification relates to the peak X-ray flux, measured by satellites, such as those operated by NOAA. Flares often occur along the neutral line between regions of opposite polarity and are associated with sunspot groups. In extreme cases, the eruption can hurl 1 billion tons of plasma into space as a coronal mass ejection. But even without a CME, the radiation from a large flare can disrupt communications and satellites on Earth. To truly appreciate the sun's ever-changing magnetic heart, we must step back and view its behavior over longer timescales. The sun experiences cycles of activity that wax and wane over roughly 11 years. During solar maximum, numerous sunspots pepper the disk, and flares and coronal mass ejections are common. During solar minimum, sunspots are scarce, and the sun appears relatively calm. The sunspot number, defined as the number of individual spots plus 10 times the number of groups, has been used since the 19th century to track the cycle. Historical records reveal that the number of sunspots varies, but follows this approximate rhythm. The cycle was first noticed by Heinrich Schwabe in the 1840s and confirmed by subsequent observers. More detailed analyses show that sunspots do not appear randomly across the solar surface. They form in two bands on either side of the equator. At the beginning of a cycle, spots emerge at mid-latitudes around 30 degrees north and south. As the cycle progresses, the bands drift toward the equator. When plotted over time, these latitudes produce the so-called butterfly diagram. Each wing of the butterfly shows a cycle, with spots appearing at higher latitudes at the start and creeping toward the equator as the cycle advances. The pattern reveals the migration of magnetic activity and offers clues to the underlying dynamo. By studying the butterfly diagram, scientists are able to infer how the interior flows redistribute magnetic flux over the cycle. There have been periods when sunspots virtually vanished for decades. One notable example is the Maunder minimum, which lasted from about 1645 to 1715. During this interval, very few sunspots were recorded, and the sun appeared exceptionally quiet. This lull coincided with a cooler period on Earth, known as the Little Ice Age. Although the causal link between solar activity and climate is complex and still debated, the coincidence illustrates the sun's influence on our environment. Observations of tree rings and ice cores show that similar periods of low activity may have occurred in the more distant past, hinting at long-term modulations of the solar dynamo. Modern observations show that the solar cycle affects more than just the appearance of sunspots. During solar maximum, the sun's magnetic field becomes more chaotic, and the number of flares and coronal mass ejections increases. Enhanced ultraviolet and soft X-ray emissions heat Earth's upper atmosphere, causing it to expand. Satellites in low Earth orbit experience increased drag and must expend fuel to maintain altitude. High-energy particles from flares can damage spacecraft electronics and pose risks to astronauts. On Earth, induced currents in power grids can cause transformers to overheat. At the same time, auroras dance farther south than usual as charged particles spiral along Earth's magnetic field lines, colliding with atmospheric molecules and producing shimmering curtains of light. The cycle, therefore, influences both our technology and our view of the night sky. Sunspots themselves have negligible impact on the sun's total light output because their darkening is balanced by bright faculae. The difference between solar maximum and solar minimum in terms of total irradiance is only about 0.15%. Nevertheless, the variation in the sun's magnetic activity can have profound effects on the heliosphere. Solar wind streams emanating from coronal holes, which are regions of open magnetic field lines, modulate cosmic ray flux and sculpt the heliospheric current sheet. The cycle also reverses the sun's global magnetic polarity. Every 11 years, when the cycle peaks, the sun's magnetic north and south poles swap places, meaning the full magnetic cycle is 22 years long. This flip underscores the dynamic and self-regulating nature of the solar dynamo. Monitoring and predicting the solar cycle require continuous observations. Networks such as the Global Oscillation Network Group, GONG, and spacecraft like the Solar Dynamics Observatory, SDO, observe oscillations and magnetic fields, providing data that helps scientists model the sun's interior flows. GONG measures the Doppler shifts of spectral lines to map flows on the surface and infer processes deep within. SDO captures images in multiple wavelengths, revealing the evolution of active regions and coronal structures. Together, these observations help forecasters predict when the sun might enter a more active or quiet phase. Yet, despite decades of study, accurately forecasting the amplitude and timing of each cycle remains difficult. The sun often surprises us with unusual behavior, reminding us that it is a complex, living system. While the long cycles of calm and chaos shape the overall rhythm, a flare is a sudden and explosive event that can catch observers off guard. Scientists have long sought indicators that could provide warnings hours or days in advance. Recent research has uncovered subtle signs that the sun may reveal before releasing a flare. Observations from NASA's Solar Dynamics Observatory detected flickering in coronal loops above active regions in ultraviolet wavelengths. These coronal loops, arcs of plasma-tracing magnetic field lines, were seen to brighten and dim erratically for several hours before flares occurred. The variability was especially pronounced in specific wavelengths, such as 131 and 304 angstroms, and the chaotic behavior started 2 to 6 hours before a flare. The intensity of the flickering was found to correlate with the strength of the ensuing flare, suggesting that the loops become increasingly unstable as they approach a breaking point. Other studies confirmed these findings, noting that variability increased by 2 to 4 times during the hours preceding a flare, and that flickering could predict medium-sized flares with up to 80% accuracy. The detection of such variability offers a promising avenue for space weather forecasting. Instead of merely counting sunspots or measuring global magnetic fields, scientists can monitor the dynamic behavior of coronal loops in real time. When combined with magnetic measurements, these observations may provide early warnings of energetic events. However, each flare is unique, and not all show the same signatures. The research emphasizes that the sun's corona is a dynamic environment, and understanding the underlying physics remains a challenge. Beyond flickering loops, instruments aboard spacecraft provide rapid warnings when a flare actually begins. For instance, the extreme ultraviolet and X-ray irradiance sensors, EXIS, on the GOES-R series of satellites are designed to detect the first hints of a flare. The EXIS instrument includes an X-ray sensor that picks up the initial bursts of high-energy photons and an extreme ultraviolet sensor that monitors fluctuations that cause Earth's atmosphere to expand. These sensors provide data to forecasters, allowing them to issue alerts when a flare is underway. By detecting the earliest X-ray emissions, EXYS can warn of an impending storm minutes before the peak energy arrives. Such early notification is critical for protecting satellites, astronauts, and power grids. Precursor signals are not limited to light. Acoustic oscillations and shifts in the photospheric magnetic field may also precede flares. Helioseismology examines how sound waves propagate through the sun, revealing internal structures and flows. Subtle changes in wave speed or amplitude might signal that a region is storing magnetic energy. Similarly, a rapid increase in magnetic shear or the emergence of new flux can serve as a warning. The challenge lies in distinguishing real precursors from the sun's constant noise. The surface is always in motion, with convection, rotation, and oscillations overlapping. Identifying patterns that consistently precede flares requires careful statistical analysis and machine learning techniques. As data accumulates, our ability to anticipate eruptions improves. Solar observers have also noted that certain types of filaments, long, dark structures suspended above the surface, become unstable before erupting. When such filaments begin to twist and kink, they may soon break away, triggering a flare or coronal mass ejection. High-resolution observations from telescopes, like the Daniel K. Inouye Solar Telescope, provide unprecedented detail of these structures. By watching them evolve, scientists hope to refine their forecasts. Ultimately, forecasting flares involves a combination of factors: the size and complexity of sunspots, the amount of magnetic shear, the appearance of emerging flux, and the dynamic behavior of coronal loops. No single indicator suffices. Rather, it is the ensemble of signals that paints a picture of the sun's mood. As we observe the sun's surface, we notice that energy release often comes after a period of seeming calm. There is a poetic tension in the way the sun moves from serenity to violence. In the hours before a flare, an active region may look relatively quiet, with only minor brightenings and motions. Yet beneath this tranquility, magnetic tension is building. The loops flicker, the magnetic field lines twist, and microflares pepper the region. To the untrained eye, nothing seems amiss. Then, a sudden flash of light erupts, and energy sweeps across the heliosphere. The contrast between the calm before the flare and the eruption itself underscores the sun's dual nature as both a nurturing and a destructive force. From a human perspective, the sun's unfailing presence at dawn and dusk conveys a sense of reliability. Yet this constancy is maintained by a delicate balance of forces. Gravity pulls inward, compressing the plasma, while radiation pressure pushes outward. In the core, fusion releases the energy needed to support the weight of the overlying layers. That energy would cause the sun to expand if gravity did not counteract it. Thus, at every point inside the sun, there is an equilibrium between inward pull and outward push. This balance has held for billions of years and will continue until the core's hydrogen is exhausted. Only then will the sun slowly evolve. But for now, the equilibrium is almost perfect. The fusion reactions not only generate photons, but also produce neutrinos, ghostly particles that rarely interact with matter. Trillions of neutrinos pass through your body every second, carrying direct information about the core's conditions. In the 1960s, detectors buried deep underground first registered these solar neutrinos. Their numbers were initially lower than theoretical predictions, leading to a mystery known as the solar neutrino problem. Subsequent experiments revealed that neutrinos oscillate between different types on their journey, resolving the discrepancy. The detection of neutrinos confirmed that the sun's energy truly comes from fusion. They provide a unique window into the otherwise inaccessible core, demonstrating that our understanding of stellar interiors is not purely theoretical. As photons diffuse through the radiative zone, their random walk transports energy outward. The time it takes for a photon to escape is so long that the light we see today began its journey long before the first humans walked on Earth. This thought bridges the gap between cosmic timescales and human histories. It reminds us that the sun's light carries the imprint of ancient events. Each photon's path is shaped by countless interactions with ions in the radiative zone, smoothing out fluctuations and leaving the surface shining steadily. Only when the plasma becomes less dense in the convection zone does energy move through mass motions rather than radiation. In the convection zone, fluid motions become the primary transport mechanism. Rising and sinking flows create patterns that repeat across the sun's surface. On the smallest scales, we see bright points where magnetic fields intensify the heat, while on slightly larger scales, mesogranulation emerges, intermediate cells that bridge granules and supergranules. These patterns are not static. They drift and evolve, merging and breaking apart. The Sun's surface is a mosaic of dynamic cells, each carrying heat and magnetic flux. The interplay of convection and magnetism is crucial for shaping sunspots, faculae, and network fields. Convection also generates the acoustic waves used in helioseismology to probe the interior. Helioseismology is the study of vibrations within the Sun. Just as seismologists use earthquakes to learn about Earth's interior, solar physicists analyze surface oscillations to infer the Sun's internal structure. The Sun rings like a bell, but the notes are not audible to human ears. These oscillations manifest as subtle pulsations of brightness and velocity across the surface. They arise from sound waves trapped inside the Sun that travel along curved paths and interfere to create standing waves. By measuring the frequencies and spatial patterns of these modes, scientists can map the temperature, density, and rotation rate deep within the Sun. Helioseismology has revealed a differential rotation profile and confirmed the depth of the convection zone. The oscillations also show that the solar interior is far from simple. Beneath the convection zone, the radiative interior rotates more uniformly, while nearer the surface, rotation rates vary with latitude. Torsional oscillations, bands of faster and slower rotation, migrate toward the equator during the solar cycle, echoing the migration of sunspots. These flows are part of the Sun's magnetic heartbeat. Helioseismology has also measured meridional circulation, a slow poleward flow at the surface, balanced by an equatorward return flow deeper down. Understanding these flows is essential for dynamo models, as they transport magnetic flux and modulate the cycle's strength and timing. The photosphere is not uniform. It shows subtle brightness variations called bright points. These tiny features correspond to concentrated magnetic flux tubes that suppress convection in their immediate vicinity, causing the surroundings to brighten. When viewed near the solar limb, the brightening becomes more pronounced because we look through longer optical paths. Bright points are building blocks of the magnetic network that outlines the edges of supergranules. They appear and disappear over minutes to hours, reflecting the continual shuffle of magnetic flux by convective flows. Although individually small, these features contribute significantly to the total magnetic energy and influence the heating of the chromosphere. Above the photosphere, spicules and fibrils shoot upward like grass blades. Spicules are thin jets of plasma that rise from the chromosphere into the lower corona, reaching heights of thousands of kilometers and lasting minutes. They transport mass and energy upward, feeding the hot corona. Fibrils, on the other hand, are elongated structures aligned with magnetic field lines that weave intricate patterns across the chromospheric landscape. These features illustrate how magnetic fields guide plasma motion. The chromosphere is a forest of fine structures, each shaped by the underlying magnetic network. In this layer, the interplay between magnetic pressure and gas pressure determines the shape and dynamics of features. On larger scales, the corona hosts loops, streamers, and coronal holes. Loops trace out the paths of closed magnetic field lines, connecting regions of opposite polarity on the surface. They glow in extreme ultraviolet and X-rays, revealing the intense heating in the corona. Streamers are tall structures above the limb, where magnetic fields fan out into the solar wind. Coronal holes appear dark in ultraviolet images. They are regions where magnetic field lines open into space, allowing high-speed solar wind streams to escape. These open fields produce fast streams that modulate cosmic rays and can interact with slower wind to form co-rotating interaction regions. The solar wind is the continuous outflow of plasma from the corona, carrying the Sun's magnetic field throughout the solar system. The discovery of the solar wind explained why comet tails always point away from the Sun, The wind interacts with planetary magnetospheres and can strip atmospheres from unprotected worlds. At Earth, the wind flows past our magnetic field, compressing it on the day side and stretching it into a long tail on the night side. Changes in the solar wind's speed, density, and magnetic orientation drive space weather. For example, a high-speed stream from a coronal hole can disturb Earth's magnetosphere for several days, producing geomagnetic storms. The combination of steady wind and sporadic eruptions shapes the heliospheric environment in which planets reside. Embedded within the solar wind are energetic particles accelerated by shocks and magnetic reconnection. Solar energetic particles can reach Earth within minutes after a flare or coronal mass ejection, posing a radiation hazard to astronauts and satellites. These particles are guided by interplanetary magnetic fields. When those fields connect back to an active region, the particles have a direct path to Earth. Predicting their arrival requires knowledge of the field topology and the properties of the acceleration process. Spacecraft like the Parker Solar Probe and Solar Orbiter are venturing closer to the Sun than any before, measuring the wind at its origin and providing clues about how particles are energized. Within the corona, magnetically closed regions store energy that can be released suddenly. The process of magnetic reconnection, where field lines tear and reconnect, converts magnetic energy into heat and kinetic energy. Reconnection occurs in thin current sheets, and often at sites where fields of opposite polarity meet. It can happen at multiple scales, from microflares to large eruptions. Recent observations with high-resolution telescopes captured reconnection events where flows exceeding 20 kilometers per second were recorded. The new loops that form after reconnection are shorter and release their tension, while the ejected material can escape into space. Reconnection is therefore a fundamental engine powering solar activity. Solar flares are classified according to their peak X-ray flux, measured in the 1 to 8 angstrom band. An X-class flare is the most intense, with flux above 10 to the -4 watts per square meter. M-class flares are moderate, and C-class flares are relatively minor. The classification gives a quick indication of the flare's potential impact on Earth. However, the magnitude alone does not determine the damage. The orientation of the magnetic fields in the associated coronal mass ejection and the speed of the shock also matter. A modest flare can produce a severe geomagnetic storm if the ejected cloud's magnetic field aligns opposite to Earth's field, allowing it to reconnect and transfer energy into our magnetosphere. The build-up to a flare can take hours or days. Active regions with complex magnetic configurations, such as delta sunspots, where opposite polarities are tightly intermingled, are prone to eruptions. Vector magnetograms reveal areas of high shear along neutral lines where the field changes direction. Sheared fields store energy like a twisted rubber band. When a trigger, such as new flux emergence or small-scale reconnection, destabilizes the region, the stored energy is released. Observers watch for the development of sigmoids, S-shaped structures in soft X-ray images that often precede flares. These shapes indicate twisted magnetic flux ropes that can erupt. Monitoring these precursors helps assess the likelihood of an imminent event. Though large flares draw attention, the Sun constantly produces small-scale events. Nanoflares and microflares occur all the time, heating the corona and maintaining its high temperature. These tiny explosions may be the collective source of coronal heating, although the idea is still debated. By studying the statistics of small flares, scientists hope to understand whether energy release follows a power law distribution, implying self-organized criticality. This perspective views the Sun as a system slowly driven toward instability by constant flux emergence and convective motions, with eruptions occurring when the system reaches a tipping point. In such systems, predicting the timing of individual events is inherently difficult, but statistical properties can be understood. Evidence from long-term observations suggests that the solar dynamo is not perfectly regular. While the average cycle length is about 11 years, individual cycles vary in duration and strength. Some cycles produce many sunspots and intense activity, while others are weaker. Researchers analyze cosmogenic isotopes like carbon-14 and beryllium-10 in tree rings and ice cores to reconstruct past solar activity. These records show longer period variations, such as the Gleisberg cycle of roughly 80 to 100 years, and the Suez cycle on timescales of centuries. The occurrence of grand minima, like the Maunder minimum, reflects the dynamo's complex behavior. The causes of these long-term modulations remain a mystery. During the Maunder minimum, sunspots were almost absent, yet auroras were still observed, indicating that the solar wind and magnetic fields continued to interact with Earth. The climate was cooler during this time, but the extent to which solar variability contributed is uncertain. Volcanic eruptions and internal climate dynamics also play significant roles. Nonetheless, understanding how changes in solar activity influence climate is important for contextualizing modern climate change. Variations in ultraviolet output affect stratospheric chemistry, and changes in cosmic ray flux may influence cloud formation. These connections are subtle and complex, but they underscore the sun's influence beyond immediate space weather effects. The butterfly diagram, which plots sunspot latitude versus time, reveals patterns that inform dynamo theories. Each cycle begins with spots appearing at mid-latitudes, around 30 degrees north and south, and as the cycle progresses, new spots emerge closer to the equator. The diagram's shape resembles butterfly wings. At solar maximum, the density of spots peaks and the wings widen. During minimum, spots disappear. The migration reflects how toroidal magnetic fields are transported and sheared by differential rotation. Comparing butterfly diagrams across cycles shows variations in width and shape that may correspond to differences in meridional flow or diffusivity. Detailed patterns help constrain dynamo models and improve predictions. Observational history also shapes our understanding. Heinrich Schwaber's discovery in 1843 of an 11-year cycle came after years of systematically counting spots. Later, Rudolf Wolff developed the sunspot number, which combines the number of individual spots and groups to provide a daily measure of activity. This index has been maintained through centuries, albeit with calibration challenges. In modern times, the International Sunspot Number and the Group Sunspot Number provide slightly different measures, and adjustments are made for observer biases. The continuity of these records is invaluable for studying long-term variations. Historical drawings, photographic plates, and more recently, satellite data enrich the archive. Predicting future cycles remains challenging. The amplitude of a cycle appears related to the strength of the sun's polar fields during the preceding minimum. Stronger polar fields may seed a stronger toroidal field and yield more sunspots. Solar cycle 24, which peaked around 2014, was relatively weak, while predictions for cycle 25 suggest moderate strength. Scientists use dynamo models to simulate the cycle, but small differences in input parameters can lead to large differences in outcomes. Data assimilation, akin to weather forecasting, may improve predictions by incorporating observations of flows, flux emergence, and polar field strength. Still, the chaotic nature of the dynamo limits predictability. The sun's influence extends beyond flares and cycles. It drives the heliosphere, a bubble carved in the interstellar medium by the solar wind. The heliosphere shields the planets from some cosmic rays, high-energy particles originating outside the solar system. When solar activity is high, the heliospheric magnetic field becomes more tangled, and cosmic ray flux at Earth decreases. During quiet periods, cosmic rays penetrate more easily. Measurements of cosmic rays recorded by neutron monitors and isotopes in meteorites reflect these variations. Understanding the heliosphere's structure has been aided by missions such as Voyager, which have crossed the termination shock and entered interstellar space, mapping the boundary of our star's influence. On Earth, we experience the sun's variability through auroras, radio blackouts, and changes in atmospheric drag. Auroras occur when charged particles precipitate along Earth's magnetic field lines and collide with atoms in the upper atmosphere. Oxygen and nitrogen emit green, red, and purple light, painting the sky with shimmering curtains. The location of auroral ovals depends on geomagnetic activity. During strong storms, they expand to lower latitudes. Radio blackouts occur when extreme ultraviolet and X-ray radiation from flares ionize the upper atmosphere, disrupting high-frequency communication. Increased drag caused by ultraviolet heating can alter satellite orbits. These effects underscore the importance of monitoring the sun to safeguard modern technology. Humanity's relationship with the sun is not merely technological. It has deep cultural and spiritual dimensions. Many ancient cultures revered the sun as a deity or as the source of life. Sun worship rituals and mythologies often reflected an intuitive recognition of its essential role. Solar eclipses, when the moon temporarily blocks the sun, were interpreted as omens. Today, our scientific understanding coexists with a sense of wonder. Watching an eclipse or a dramatic aurora connects us with ancestors who gazed at the same sky. The sun's cycles of light and darkness continue to shape human rhythms, from agriculture to sleep patterns. Recognizing this continuity fosters a reverence for our star. Recent instruments push the boundaries of solar observation. The Parker Solar Probe, launched in 2018, periodically dives to within a few million kilometers of the sun's surface, flying through the corona and sampling the solar wind at its birthplace. Its instruments measure fields and particles at close range, revealing turbulence and wave-particle interactions. The Solar Orbiter mission complements these measurements with high-resolution imaging and remote sensing from inside the orbit of Mercury. Together, these missions provide a three-dimensional view of the sun's atmosphere. They also coordinate with Earth-based observatories, creating a network of observations that span multiple scales and perspectives. Ground-based telescopes like the Daniel K. Inouye Solar Telescope, DKYST, capture the sun with unprecedented detail. DKIST's 4-meter mirror resolves structures as small as 30 kilometers across, allowing scientists to observe magnetic fields in individual granules and spicules. Such fine resolution reveals the complexity of magnetic flux tubes and how they twist and writhe. Combined with spectropolarimetry, DKIST measures the vector magnetic field, providing clues to the small-scale dynamo. Observations of microflares and jets test theories of energy release. Coordinated campaigns involving DKIST, space telescopes, and radio arrays like LOFAR and the VLA produce multi-wavelength views that capture the interplay of phenomena across the solar atmosphere. Spectroscopy is another key tool for understanding the sun. By analyzing the light at different wavelengths, scientists can determine temperatures, densities, and velocities of solar plasma. Doppler shifts reveal flows, while line profiles indicate turbulence. In the photosphere, spectral lines of iron and sodium show granulation patterns and oscillations. In the chromosphere, the H-alpha line captures filaments and prominences. In the corona, emission lines from highly ionized iron reveal temperatures of millions of degrees. Spectropolarimetry adds information about magnetic fields by measuring the polarization of light. These techniques allow us to infer conditions in regions where direct measurements are impossible. Magnetic fields on the Sun exhibit a variety of configurations. Bipolar regions consist of two main spots of opposite polarity, connected by loops. Unipolar regions contain dispersed fields of one sign. Filaments mark long, horizontal fields suspended in the chromosphere, while coronal holes mark open field lines. The distribution and complexity of these fields determine the likelihood of eruptions. Statistical studies show that regions with high magnetic complexity produce more flares. However, complexity alone is not sufficient. The orientation of fields relative to the overlying coronal arcade and the rate of flux emergence also matter. Accurate prediction requires monitoring vector fields and modeling how they evolve. In addition to flares, the Sun ejects huge clouds of plasma known as coronal mass ejections, CMES. CMEs can expel billions of tons of material into space at speeds of hundreds to thousands of kilometers per second. They carry magnetic fields that can interact with Earth's field, triggering geomagnetic storms. Some CMEs are associated with flares, while others originate from the eruption of filaments or the opening of closed fields. The fastest CMEs often occur during solar maximum. The arrival time of a CME at Earth depends on its speed and the conditions of the solar wind. Predicting this arrival is crucial for preparing for potential impacts on satellites and power grids. When a CME interacts with Earth's magnetosphere, the resulting geomagnetic storm can induce currents in power lines. These geomagnetically induced currents, GICS, can overload transformers and cause blackouts. In March 1989, a powerful storm triggered by a CME caused the collapse of Quebec's power grid. Since then, utilities have developed mitigation strategies, such as monitoring space weather and adjusting grid operations during storms. Still, the increasing reliance on electricity and long transmission lines increases vulnerability. Understanding the solar sources of CMEs and improving prediction models help reduce these risks. Space weather forecasting is thus not only a scientific endeavor, but also a practical necessity. Space weather also affects aviation and communication systems. High-frequency radio signals used by aircraft to communicate over polar routes can be disrupted by ionospheric disturbances during solar events. When communication is unreliable, flights may be rerouted to lower latitudes, increasing travel time and fuel consumption. Satellites used for navigation, such as GPS, rely on signals traveling through the ionosphere, and fluctuations in electron density can delay or refract these signals, reducing accuracy. Radiation from solar energetic particles can damage satellite components and degrade solar panels. Monitoring the Sun and issuing timely alerts allows operators to place satellites in safe modes and adjust flight paths. Astronauts in space face additional risks. Outside Earth's protective atmosphere and magnetic field, they are exposed to increased radiation from solar particles. During a solar storm, radiation levels can rise significantly. On the International Space Station, astronauts can retreat to shielded areas to reduce exposure. For missions to the Moon or Mars, shielding and forecasting become even more critical. Understanding the timing and intensity of solar storms helps mission planners design safe operations. Future exploration will rely on a network of space weather monitors at various points in the solar system to provide early warnings to spacecraft and habitats. The Sun's magnetic field not only shapes its own atmosphere, but also extends far into space. The heliospheric current sheet, a wavy surface where the polarity of the field changes, wraps around the Sun like a ballerina's skirt. As the solar wind carries the field outward, the Sun's rotation twists it into a spiral known as the Parker spiral. Planetary magnetospheres and interplanetary dust interact with this spiral. Comets, with their long tails, reveal the direction of the local field. Observations from spacecraft show that the current sheet's tilt and thickness vary over the cycle, influencing cosmic ray propagation and solar wind turbulence. At times, the Sun reminds us of its capacity for superstorms. The Carrington event of 1859 is the most famous example. An intense flare and CME struck Earth, causing auroras visible near the equator and inducing currents that damaged telegraph systems. If a similar event occurred today, the impact on power grids and satellites would be severe. In 2012, a CME comparable in size to the Carrington storm missed Earth by about 9 days, passing through the orbit where Earth had been earlier. Such near misses highlight the need to understand extreme events and to build resilience. The study of old auroral records and tree ring anomalies helps identify past superstorms. Our awareness of solar hazards has led to the development of early warning systems. The National Oceanic and Atmospheric Administration, NOAA, operates the Space Weather Prediction Center, which issues alerts based on data from satellites like the GOES series, the Deep Space Climate Observatory, and the Solar and Heliospheric Observatory. These instruments monitor the Sun's X-ray flux, coronal imagery, and interplanetary magnetic fields. When the X-ray sensor on GOES detects a sudden increase in flux, it triggers an alert for a flare. Observatories around the world contribute data to global networks, and international collaboration ensures that warnings reach all stakeholders. Space weather forecasting is an evolving discipline that incorporates physics, statistics, and artificial intelligence. The study of magnetism on the Sun has broad implications. Magnetic fields are fundamental to many astrophysical processes, from star formation to the dynamics of galaxies. The Sun is our nearest laboratory for magnetohydrodynamics, allowing us to test theories under conditions that cannot be reproduced on Earth. Lessons learned from solar physics inform our understanding of other stars. For instance, rapidly rotating young stars have more vigorous dynamos and produce stronger flares. Red dwarf stars can exhibit superflares orders of magnitude more energetic than anything seen on the Sun, raising questions about the habitability of planets around them. By studying our star, we gain context for the diversity of stellar behavior. The energy produced in the core travels outward, not only as photons, but also as neutrinos. These ghostly particles are so weakly interacting that they pass through the Sun and Earth almost unhindered. Early experiments deep underground detected fewer solar neutrinos than expected, leading to the famous solar neutrino problem. It was later solved when physicists discovered that neutrinos can change flavor as they travel, reducing the number observed. The detection of neutrinos from the Sun provides direct evidence that fusion is indeed occurring in the core and offers a way to monitor the Sun's energy production in real time. Future neutrino observatories will refine our understanding of the nuclear reactions at the heart of our star. Equally important is the balance of forces within the Sun. Gravity pulls the material inward, trying to collapse the star, while the pressure produced by hot gas and radiation pushes outward. This balance, known as hydrostatic equilibrium, maintains the Sun's spherical shape and stable radius. If fusion were to slow, gravity would compress the core, raising the temperature and pressure and restoring the fusion rate. If fusion increased, the core would expand and cool. This self-regulating feedback ensures that the Sun remains stable over long timescales. Understanding this delicate balance helps us appreciate why the Sun appears steady and reliable, even though it is a restless ball of plasma. Deep in the radiative zone, the plasma is so dense and ionized that atoms are stripped of most electrons. The opacity of this region depends on the abundance of elements heavier than helium, called metals. These elements absorb and scatter photons, impeding their progress. Small changes in metallicity can alter the structure of the radiative zone and the overall luminosity of the Sun. Measuring the composition is challenging, but helioseismology and spectroscopy provide clues. These techniques reveal that the solar interior has slightly different abundances than previously thought, prompting revisions to models. The interplay between composition, opacity, and energy transport illustrates the complex physics that shapes the Sun's interior. The study of solar oscillations has opened a window into the interior. The Sun rings with millions of resonant modes, like a musical instrument. Acoustic waves generated by convection travel through the interior and reflect at the surface, creating standing waves. By measuring the frequencies and travel times of these modes, helioseismologists infer the temperature, density, and rotation profiles at different depths. This field has revealed differential rotation inside the Sun and detected flows that transport magnetic flux. Instruments such as the Global Oscillation Network Group and the Helioseismic and Magnetic Imager on the Solar Dynamics Observatory continually record oscillations. Their data have transformed our understanding of solar structure. Above the photosphere lies the chromosphere, a region of rising temperature and dynamic activity. Here, slender jets called spicules shoot upward at speeds of tens of kilometers per second, reaching heights of several thousand kilometers before falling back. Spicules carry mass and energy into the corona and may contribute to heating. Fibrils and mottles weave a fine pattern across the chromosphere, tracing magnetic field lines. Between bright network elements, dark filaments outline channels of cooler plasma. These features reveal the interplay of magnetic fields and plasma flows. Observing them requires narrowband filters and high-speed cameras to capture their rapid evolution. The outer atmosphere, or corona, is a realm of paradox. It extends millions of kilometers into space and glows in ultraviolet and X-ray wavelengths. Despite being farther from the heat source, it reaches temperatures of 1 to several million degrees, much hotter than the photosphere. The coronal heating problem remains a central puzzle. How is the plasma heated to such high temperatures? Proposed mechanisms include the dissipation of waves generated by convection and the release of magnetic energy through reconnection of small loops, sometimes called nanoflares. Coronal loops, streamers, plumes, and holes reflect the structure of the magnetic field. Observations from instruments like the Solar and Heliospheric Observatory and the Parker Solar Probe continue to probe this enigmatic region. Magnetic fields on the Sun emerge from the convection zone as bundles of flux called flux tubes. Buoyancy causes these tubes to rise through the plasma, twisting and expanding as they approach the surface. When they break through the photosphere, they form pairs of sunspots with opposite polarity. The area between these spots is an active region where flares often originate. The shape and complexity of the emerging flux influence the likelihood of flares. Smaller bundles may form pores or network fields, while larger loops create extended active regions. The dynamics of flux emergence are studied through simulations and observations. helping us understand how magnetic energy builds up before it is released. Within the corona, cool, dense plasma can become suspended along magnetic field lines, forming prominences that appear as bright arches when seen at the solar limb. When viewed against the disk, these same structures appear as dark filaments because they absorb light. Prominences can persist for weeks, changing shape as they sway in response to waves and flows. Some erupt violently, releasing plasma into space and triggering coronal mass ejections. Others remain stable until the magnetic field supporting them reconfigures. Studying prominences helps scientists understand how magnetic structures support mass against gravity and how they store and release energy. Not all magnetic reconnection events produce large flares. Observations have revealed a spectrum of smaller events, ranging from microflares to nanoflares. These small bursts occur frequently and may contribute significantly to coronal heating. The Inouye Solar Telescope recently captured a microflare where opposite magnetic fields reconnected in a region less than 1,000 kilometers wide, releasing energy equivalent to billions of lightning bolts and driving plasma flows exceeding 20 kilometers per second. Such events illustrate the diversity of energy release on the Sun and highlight the importance of high-resolution observations. Solar flares vary enormously in energy. The smallest, called A-class flares, barely register above the background X-ray level, while the most powerful X-class flares can release energy comparable to hundreds of billions of atomic bombs. The classification into A, B, C, M, and X classes is based on the peak X-ray flux measured by GOES satellites. Each step up in class represents a 10-fold increase in intensity. Within these classes, the number following the letter gives a finer scale. An M5 flare is 5 times more intense than an M1. Such classifications provide a convenient shorthand for space weather forecasters. However, the energy released is not limited to electromagnetic radiation. Flares also accelerate particles and can drive shockwaves in the corona. Flares often occur in concert with coronal mass ejections, but the relationship is complex. Some flares are confined, meaning that the magnetic field rearranges locally without ejecting large amounts of plasma. Others are eruptive, associated with a CME that expels billions of tons of material into space. The conditions that determine whether a flare will accompany a CME involve the geometry of the overlying field and the amount of twist in the flux rope. Understanding this relationship is important because CMEs can cause geomagnetic storms when they interact with Earth's magnetosphere. Advances in modelling are beginning to simulate coupled flare CME events, linking magnetic reconnection to large-scale eruptions. Our Sun's flares are dwarfed by the superflares observed on some stars. Space telescopes like Kepler and TESS have recorded flares on solar-like stars that are thousands of times more energetic than the strongest solar events. These superflares may be driven by exceptionally strong magnetic fields, or by interactions with close-in planets. Although the Sun appears less prone to such extremes, historical records hint at rare events approaching that scale. Studying stellar superflares helps place the Sun's activity in context and informs the search for life beyond the solar system. It also reminds us that stellar magnetism can manifest in surprising ways. The 11-year solar cycle can be described by models that incorporate differential rotation and meridional flows. In the Babcock-Layton framework, toroidal magnetic fields created by shear at the tachocline give rise to sunspot pairs. As these spots decay, they release magnetic flux that is transported toward the poles by meridional flows. This polar field then forms the seed for the next cycle's toroidal field. The cycle of amplification, emergence, decay, and reversal results in the observed periodicity. Variations in the strength of these processes lead to differences in cycle amplitude and shape. Understanding this chain of events is essential for predicting future cycles. Beyond the familiar 11-year rhythm, the Sun exhibits longer-term variations. The Gleisberg cycle, lasting about 80 to 90 years, modulates the amplitude of individual cycles. The Suez or de Vries cycle spans roughly 200 years. Evidence for these cycles comes from records of sunspot numbers, cosmogenic isotopes like carbon-14 in tree rings, and beryllium-10 in ice cores. During the Maunder minimum in the 17th century, sunspots were exceedingly rare, and temperatures in parts of the northern hemisphere were lower than usual. These long-term changes reveal that the solar dynamo can operate in different modes. They also raise questions about how solar variability influences Earth's climate. One of the most promising predictors of the next cycle's strength is the magnetic field at the Sun's poles. Observations show that cycles following strong polar fields tend to be more active. After sunspot maximum, the meridional flow carries decayed flux to the poles, building the polar field. Instruments like the Wilcox Solar Observatory have measured these fields for decades, providing a record that helps forecast future cycles. The current cycle, Solar Cycle 25, began in 2019 and is predicted to peak around 2025. Early signs suggest it will be moderate in strength. Watching the polar fields develop provides clues about the coming cycle and helps test dynamo models. When a geomagnetic storm hits Earth, currents are induced in long conductors like power lines and pipelines. These geomagnetically induced currents can overheat transformers and cause blackouts. Modern power grids are complex and interconnected, making them susceptible to disruption. Airlines adjust flight paths during solar storms to minimize radiation exposure and communication disruptions. Satellites can be damaged by energetic particles and suffer drag from an expanded atmosphere. To mitigate these impacts, operators rely on forecasts and may power down sensitive systems or switch to safe modes. Investing in resilient infrastructure and backup systems is essential as our dependence on technology grows. Observing the Sun requires a fleet of space-based observatories. The Solar Dynamics Observatory provides high-resolution images in multiple wavelengths, revealing the fine structure of the atmosphere. The GOES satellites carry the X-ray sensor and extreme ultraviolet sensor, which detect the first hints of a flare and monitor the ultraviolet flux that heats Earth's upper atmosphere. The stereo spacecraft view the Sun from different angles, allowing three-dimensional reconstruction of CMEs. Parker Solar Probe ventures closer to the Sun than any mission before, sampling the solar wind and measuring electric and magnetic fields. Each of these missions contributes unique data that feed into models and improve our situational awareness. Modern forecasting increasingly employs machine learning. Algorithms are trained on past flares, magnetic field measurements, and coronal images to identify patterns that precede eruptions. Neural networks, random forests, and probabilistic classifiers are among the techniques used. These models can handle large datasets and may uncover subtle features overlooked by human analysts. However, they require careful validation and cannot substitute for physical insight. Combining data-driven methods with theoretical models offers the best prospects for reliable predictions. As computing power grows and datasets expand, artificial intelligence will play a larger role in space weather forecasting, complementing the expertise of scientists. The Sun's light is also the primary energy source for Earth's climate system. Its radiative output sets the baseline for global temperature. While variations across the cycle are small, they are not zero, and changes in ultraviolet radiation influence the stratosphere. The sun's brightness has gradually increased over geological time as the core has converted hydrogen to helium, and its future evolution will affect life on Earth. In a few billion years, as the core hydrogen is depleted, the sun will expand into a red giant. Its outer layers will engulf the inner planets, and Earth's oceans will boil away. These long-term changes remind us that our planet's habitability is tied to the life cycle of our star. The interplay between science and art emerges in solar observations. Images of the sun's surface and corona reveal patterns that inspire awe and artistic expression. From the swirling cells of granulation to the delicate arcs of prominences, the sun's forms evoke biological and cosmic analogies. Musicians have translated solar oscillations into sound, giving humans a way to listen to the star's heartbeat. Visual artists have used solar spectra to create color palettes. Such creative engagements bridge the gap between technical understanding and human experience, making the sun more accessible to the wider public. Education and outreach are essential for fostering appreciation of solar science. Planetarium shows, public observatories, and citizen science projects invite people to observe sunspots, track the cycle, and contribute to data collection. Projects like Sunspotter ask volunteers to classify sunspot complexity, aiding research into flare prediction. Amateur astronomers, equipped with solar filters and specialized telescopes, can safely observe the sun and share their observations. Engaging the public not only enriches scientific data, but also builds awareness of space weather hazards and the need for preparedness. Solar physics also intersects with technology development. Instruments must operate in extreme conditions of heat and radiation. Innovations in heat shielding, optics, and detectors developed for solar missions often find applications elsewhere. The Parker Solar Probe uses a heat shield made of carbon-carbon composite to withstand temperatures over 1,000 degrees Celsius. Advances in adaptive optics, which compensate for atmospheric distortion, allow ground-based telescopes to achieve sharp solar images. Satellite platforms developed for solar observation contribute to Earth observation and astrophysics. Thus, studying the sun drives technological progress with broader benefits. As we investigate the sun's inner workings, we encounter questions that remain unsolved. What mechanism heats the corona to temperatures millions of degrees hotter than the photosphere? How do small-scale magnetic fields emerge and evolve? What sets the amplitude and period of the solar cycle? Can we predict solar storms with greater accuracy? These questions challenge our understanding of plasma physics and complex systems. They motivate new theories and new instruments. Each discovery reveals deeper layers of complexity, reminding us that the sun still holds secrets despite centuries of study. The subtle signs of an impending flare are a field of active research. Beyond the flickering of coronal loops, scientists are exploring whether changes in the ratios of emission lines, shifts in the distribution of acoustic power, or the emergence of specific patterns in magnetograms could signal an approaching eruption. Machine learning algorithms are being trained on historical data to recognize patterns that human eyes may miss. Some models analyze the evolution of magnetic complexity, while others focus on temporal sequences of images. The goal is to provide reliable forecasts hours in advance so that satellites can be protected, astronauts warned, and electric grids prepared. This research emphasizes that early warning is probabilistic rather than deterministic. The sun is a chaotic system, and small changes can lead to vastly different outcomes. A region may display all the hallmarks of instability, yet remain quiet, while a seemingly benign region may suddenly erupt. Forecasting thus involves estimating the likelihood of events and quantifying the uncertainty. Users of space weather forecasts, such as satellite operators and airlines, make decisions based on these probabilities, balancing risk and cost. As our models improve, the confidence intervals narrow, but uncertainty will always be present. The process of magnetic reconnection, responsible for flares, also occurs in other environments. In Earth's magnetotail, reconnection powers auroras. In laboratory plasmas, reconnection influences confinement. Studying the Sun provides a natural laboratory with a range of conditions, from low beta corona to high beta photosphere. Experiments like the Magnetic Reconnection Experiment, MRX, replicate aspects of solar reconnection in controlled settings. Comparing laboratory results with solar observations deepens our understanding of energy conversion in plasmas. The universality of reconnection underscores the interconnectedness of physical processes across the universe. The solar dynamo may also operate in layers closer to the surface than once thought. Simulations suggest that convective motions in the upper convection zone can amplify and organize magnetic fields, producing patterns resembling observed sunspots. If confirmed, this shallow dynamo would explain why sunspot emergence often occurs near the surface and would affect our understanding of cycle variability. The idea challenges older theories that place the dynamo near the base of the convection zone. Ongoing research aims to reconcile observations of surface flows, helioseismic measurements, and numerical models to determine where and how the Sun's magnetic field is generated. Our knowledge of the Sun has grown through technological advances, but it is also built on patience. Long-term monitoring is essential to capture cycles and rare events. Instruments must survive in space for decades, and data archives must be preserved and calibrated. The International Sunspot Number has been maintained for over 2 centuries. The Wilcox Solar Observatory has measured the Sun's magnetic field since the 1970s. These long records enable the identification of trends and anomalies. They also highlight the importance of continuity in science. Future missions must plan for similar longevity to continue unraveling the Sun's mysteries. As we look to the future, we envisage instruments that will peer deeper into the Sun and capture finer details. Plans include next-generation coronagraphs to image the corona close to the solar limb, and magnetographs that can resolve fields on scales of a few kilometers. Arrays of radio antennas will map plasma oscillations and particle acceleration. At the same time, advances in computing will enable more realistic simulations that couple the convection zone, photosphere, chromosphere, and corona. These models will incorporate radiative transfer, magnetohydrodynamics, and kinetic effects, providing holistic pictures of solar phenomena. The synergy between observation and simulation will be key. The Sun's story is intertwined with the planets that orbit it. Mercury is scorched by intense radiation and has a tiny, eroded magnetic field. Venus has a dense atmosphere that shields its surface but also drives a runaway greenhouse effect. Earth's magnetic field and atmosphere make it uniquely habitable, but they are vulnerable to solar storms. Mars lost its global magnetic field early in its history, and the solar wind stripped away much of its atmosphere. Studying how each planet interacts with the solar wind helps us understand the requirements for habitability and informs the search for life elsewhere. It also reminds us of the delicate conditions that allow life to flourish. Our appreciation for the Sun grows when we consider its context among stars. The Sun is a G-type main sequence star, neither especially massive nor especially dim. Its stability and longevity have allowed life to evolve on Earth. Comparing the Sun to other stars reveals diversity in magnetic activity. Some stars rotate faster and exhibit strong flaring activity. Others are more quiescent. Understanding where the sun lies in this spectrum helps us evaluate whether our star is typical or unique. Observations of solar twins, stars with similar mass, age, and composition, allow us to test theories of stellar evolution and activity. At the heart of all this exploration is a sense of curiosity and wonder. The sun is our closest star, yet its complexity rivals that of the most distant phenomena. Each new discovery opens doors to new questions. We have glimpsed the mechanisms that power flares and shape cycles, but many details remain elusive. By continuing to observe, analyze, and model, we refine our understanding and prepare for surprises. The sun invites us to look up, to think deeply about natural processes, and to appreciate the interplay between chaos and order that underlies its behavior. In the hours leading up to a flare, the sun may whisper in subtle ways. A faint flicker, a shift in magnetic alignment, or a change in oscillation patterns may hint at the coming storm. Instruments tuned to different wavelengths and sensitive to minute fluctuations listen for these whispers. Sometimes they detect a crescendo of variability before the flare begins. Other times, the eruption arrives without warning. The science of anticipation is still developing. For now, observers continue to watch the sun with a mix of vigilance and humility, knowing that nature often behaves unpredictably. When a flare does erupt, the release of energy is both destructive and beautiful. The sudden brightening outshines all other sources of X-rays in the solar system. Particles accelerate along magnetic field lines, producing intense radio bursts. The flare's light sweeps across space, reaching Earth 8 minutes later. In its wake, shock waves propagate through the corona, and loops rearrange themselves. For a brief moment, the sun's complexity becomes visible, and we witness a snapshot of cosmic energy at work. Such scenes remind us that our star, though familiar, remains a source of awe. After the flare subsides, the sun returns to its perpetual rhythm. Granules continue to bubble, magnetic fields continue to emerge, and the cycle continues its slow march. Each flare leaves behind rearranged fields and energized plasma that slowly relax. The aftermath can last hours or days as the corona cools and the solar wind carries away the debris. Observing these relaxation processes provides insight into energy dissipation and plasma cooling. The interplay between impulsive events and long-term evolution is a fundamental aspect of solar dynamics. As we conclude this chapter of our exploration, we reflect on how far humanity has come in understanding the sun. From ancient myths to modern satellites, our relationship with the star has evolved from reverence to scientific inquiry, without losing its sense of wonder. We now know that the sun is not a static lamp, but a dynamic engine of plasma and magnetic fields, continuously shaping the environment around it. Every discovery adds depth to this narrative, weaving a tapestry of science and story that connects us to the cosmos. Our exploration of the sun's complex personality highlights its role as a living, dynamic system. Every granule that blooms and fades on the photosphere, every loop of magnetic field that emerges and reconnects, and every oscillation that rings through its interior contributes to the overall rhythm. The sun is not merely a distant lamp, but an active star that influences our planet and the broader solar system. It fuels life on Earth and drives space weather that can threaten our technology. Understanding the sun's cycles, surface patterns, magnetic fields, and flares is therefore more than an academic pursuit. It is essential for our civilization's resilience. Throughout this narrative, We have journeyed from the heart of the Sun, where fusion powers its luminosity, to the outer atmosphere, where magnetic fields sculpt luminous arcs and violent eruptions. We have explored the convection that churns beneath the surface, creating the patterns we see in granules and sunspots. We have examined how the Sun's magnetic heartbeat leads to cycles of calm and chaos, and how subtle signs can foreshadow spectacular flares. In the next part of this documentary, we will delve even deeper into the physics of solar storms, trace how the energy of a flare interacts with the interplanetary medium, and investigate how these cosmic storms impact Earth's magnetosphere. For now, we leave you with the image of a star that never rests, its surface alive with motion, and its magnetic heart pulsing with mysterious power. The journey has only begun, and the mysteries continue to deepen ever. The Sun's surface is a restless sea of light and plasma, its granulated texture hiding currents of magnetism that twist and coil beneath. Every rotation drags the magnetic field lines with it, winding them up like a set of invisible springs. Darker regions known as sunspots mark places where these fields pierce the visible surface, creating localized zones of intense magnetism and cooler temperature. Over days and weeks, the differential rotation and bubbling convective motions increase the tension in these magnetic fields, storing energy in patterns more complex than any machine. Within these sunspot groups, magnetic strands arc out into the hot, rarefied corona, connecting positive and negative regions like loops of elastic. The continuous motion of plasma distorts these loops, causing them to wrap around one another and occasionally fold back on themselves. Scientists have compared this process to twisting a rubber band. The more it is turned, the more energy it stores, and the more explosive its snap will be. As the loops become tangled, the pressure of trapped plasma within them rises, heating the surrounding atmosphere and creating bright, active regions visible even to amateur astronomers. Viewed from a distance, the build-up of magnetic tension is gradual and almost serene. On the Sun's scale, it is like watching mountain ranges slowly buckle. Though invisible to the eye, the underlying forces accumulate relentlessly. Each region of twisted field has its own character, shaped by the geometry of the sunspot pair beneath. Some loops reach thousands of kilometers above the surface, while others remain low and dense, yet all contribute to a global network of tension that constantly reshapes itself. This constant rearrangement ensures that no 2 days on the Sun are identical. Flares tend to occur near the peaks of the solar cycle, when sunspots are abundant and magnetic complexity is greatest. During these times, the tangled fields in active regions are especially stressed, and the probability of an eruption increases. Yet the Sun never waits for our convenience. Smaller flares and microflares can erupt even during periods of relative quiet, each releasing energy equivalent to millions of nuclear bombs. In the months leading up to a major flare, instruments record subtle changes in the pattern of magnetic fields, hinting at the unseen warping taking place beneath the photosphere. The energy stored in a twisted magnetic structure dwarfs anything we experience on Earth. The European Space Agency notes that when these twisted fields finally release, they heat solar material to millions of degrees and produce bursts of radiation across the electromagnetic spectrum. This heating occurs over volumes hundreds of times larger than our planet, and yet it happens in a matter of minutes. The comparison often made is to a billion hydrogen bombs exploding simultaneously, but even that fails to convey the scale. For those watching from afar, the rising tension manifests as subtle brightening and an unusual twisting of coronal loops. Researchers have quantified the classes of solar flares using a lettered system that measures the peak X-ray brightness. A-class flares are the weakest, followed by B, C, and M, while the most powerful events are labelled X. Each successive letter represents a tenfold increase in energy output. Within each class, a number from 1 to 9 gives further refinement, so an M5 flare is 10 times stronger than an M4. Although the letters sound simple, the differences in radiated power are enormous. An X10 flare can release nearly 100 times the energy of an X1 event. While magnetism provides the framework, the sun's convection drives the motion that creates stress. Hot plasma rises, cools and sinks in a pattern that looks like boiling water, carrying magnetic field lines along. The equator rotates faster than the poles, causing the global magnetic field to twist over the course of the 11-year solar cycle. Differential rotation not only stretches field lines, but also encourages them to break and reconnect, seeding active regions with complex loops. Without these motions, the sun would be a far less interesting star. Astrophysicists compare the pre-flare coronal loops to twisted ropes that glow in ultraviolet light. Observatories like NASA's Solar Dynamics Observatory watch these ropes twist, writhe, and occasionally erupt. The loops often appear as arches anchored in sunspots, and their movement hints at the enormous forces at play. Some loops kink or twist into helical shapes, a sign that the underlying magnetic field is approaching a threshold. When that threshold is reached, an eruption becomes inevitable. Near the surface, magnetic stress can accumulate for weeks, but it is often a sudden disturbance that triggers release. A neighboring active region may evolve, sending waves through the corona that destabilize a delicate balance. On other occasions, the steady shearing motion of plasma slowly increases the twist until the field can no longer contain itself. Observers sometimes see filamentary structures, cool, dark threads suspended by magnetic fields, begin to rise. These filaments signal an impending eruption. As the filament lifts, it drags field lines with it, increasing tension even further. Magnetic helicity is a measure of the twist and linkage of magnetic field lines, and it accumulates like an unseen currency in active regions. When helicity becomes large enough, the region is prone to erupt. Studying the evolution of helicity helps forecasters estimate when a flare might occur. Despite decades of research, predicting the exact moment remains challenging because the interplay of forces is chaotic and sensitive to small perturbations. This uncertainty adds to the intrigue, making each event a surprise. When the threshold is crossed, the release is rapid. Magnetic reconnection occurs when field lines of opposite direction are pressed together and exchange partners, snapping into a new configuration. The energy stored in the twist is suddenly converted into heat, kinetic motion, and radiation. Laboratory experiments have recreated reconnection on small scales, but the sun's version is far more violent. In the reconnection region, electrons and ions are hurled in opposite directions along newly formed field lines, carrying away energy at tremendous speeds. The concept of reconnection has been refined through direct observations. In recent years, NASA's Parker Solar Probe and the European Solar Orbiter have flown closer to the Sun than any previous spacecraft. Measurements from these missions revealed signatures of field lines breaking and reconnecting in the corona. They saw jets of particles and sudden reversals in magnetic orientation, confirming that reconnection drives much of the Sun's explosive activity. These findings support decades of theory and help scientists understand how energy cascades from large scales to small. During reconnection, loops of magnetic field detach from the surface and snap together, releasing loops of heated plasma known as flare arcades. The region where reconnection occurs becomes a cauldron of accelerated particles. Protons and electrons are whipped to near light speed, forming beams that follow the newly reorganized field lines. As they spiral, they generate intense electric currents and set up shocks that propagate outward. The whole process unfolds in seconds, yet the energy release continues for minutes to hours as the magnetic configuration relaxes. One way to visualize reconnection is to imagine two loops of twisted rope lying next to each other. If the ropes are pulled together, their strands may slip and intertwine, creating new loops. In the corona, the loops are made of magnetic lines, and the pulling force comes from the pressure of hot plasma. When reconnection occurs, the new loops snap back like released springs, flinging plasma outward and upward. This analogy helps explain why reconnection is so efficient at accelerating particles and converting stored magnetic energy into other forms. As electrons and ions accelerate, they radiate energy across a broad spectrum. The first sign of a flare in high-energy wavelengths is often a burst of X-rays. Soft X-rays come from superheated plasma at tens of millions of Kelvin, while hard X-rays originate from non-thermal electrons colliding with dense material. These interactions produce Bremsstrahlung radiation, photons emitted when charged particles are decelerated by electric fields. Because the Sun's atmosphere is thin, high-energy electrons travel long distances before losing energy, making the hard X-ray signal a direct probe of particle acceleration. Gamma rays can also accompany strong flares. When accelerated protons and heavy ions collide with atomic nuclei in the Sun's atmosphere, they can produce gamma rays through nuclear interactions. These gamma rays carry information about the highest energy particles in the flare. Observatories like the Fermi Gamma Ray Space Telescope detect these photons and use them to infer the number and energy of accelerated ions. Meanwhile, radio telescopes on Earth observe bursts at lower frequencies, tracing beams of electrons streaming through the corona. Optical and ultraviolet light show the flare in more familiar colors. In white light, a flare appears as a sudden bright patch on the solar surface, sometimes accompanied by a bright ribbon that spreads along the neutral line between sunspot polarities. Ultraviolet emissions reveal the heating of the chromosphere and transition region, where temperatures jump from thousands to millions of degrees. Instruments like the Atmospheric Imaging Assembly on the Solar Dynamics Observatory capture these changes with high temporal resolution, allowing researchers to study the evolution of flare ribbons and post-flare loops. Radio emission arises when accelerated electrons spiral around magnetic field lines at near light speed. The frequency of emission depends on the local magnetic field strength. Stronger fields near the surface produce higher frequencies, while weaker fields near the surface produce lower frequencies. Fields in the outer corona produce lower frequencies. During flares, different types of radio bursts occur. Type 2 bursts drift slowly to lower frequencies and are associated with shock waves moving through the corona. Type 3 bursts are brief and descend rapidly in frequency as beams of electrons escape along open field lines. These radio signatures offer clues about how particles escape the Sun. Flares often accompany coronal mass ejections, but they are distinct phenomena. A flare is a burst of electromagnetic radiation. A coronal mass ejection, or CME, is an enormous eruption of plasma and magnetic field from the corona. CMEs eject billions of tons of material, mostly protons and electrons, into space, along with a tangle of magnetic field lines. They can travel at speeds from a few hundred to several thousand kilometers per second, depending on the energy released and the background solar wind. The largest CMEs can reach Earth in less than a day. The origin of a CME is closely linked to the magnetic structures that produced the flare. Twisted magnetic flux ropes anchored in the photosphere can become unstable if their tension exceeds the restraining forces. When reconnection occurs beneath the rope, it detaches and begins to rise. As it accelerates, The rope drags plasma with it, forming a gigantic bubble that expands through the corona. Once free, the CME carries its own embedded magnetic field, sometimes stronger than the ambient solar wind. A CME can generate a shock wave if it travels faster than the surrounding solar wind. This shock accelerates particles in front of it, creating a hail of high-energy protons and heavier ions. These energetic particles, sometimes called solar energetic particles, can reach Earth within tens of minutes of the eruption. Because they travel along magnetic field lines, they can penetrate the polar regions of Earth's magnetosphere, posing radiation hazards to astronauts and high-flying aircraft. Ground-based instruments detect these storms as sudden increases in cosmic ray intensity. Space agencies monitor CMEs using coronagraphs, telescopes that create artificial eclipses to block the sun's bright disk. Instruments on spacecraft, such as the Solar and Heliospheric Observatory, SOHO, and the STEREO twins, provide images of CMES as they expand into space. Data from these instruments allow forecasters to estimate the speed, direction, and size of an eruption, and thus determine if it is likely to impact Earth. When a CME is Earth-directed, it can compress our planet's magnetosphere and trigger geomagnetic storms. The severity of a geomagnetic storm depends on the orientation of the magnetic field carried by the CME. If the field is oriented southward, opposite to Earth's northward field, magnetic reconnection can occur at the dayside magnetopause. This allows energy and particles to penetrate deep into the magnetosphere, causing auroras and disturbances in electrical systems. Conversely, a northward-oriented field may slide past with little effect. The orientation is difficult to know until the CME arrives, adding uncertainty to space weather forecasts. Not all flares produce CMES, and not all CMES are accompanied by flares. Some CMEs emerge slowly from quiescent filament channels without any brightening, while others are driven by the same magnetic reconnection that triggers a flare. Observations suggest that the energy threshold for a CME is related to the amount of helicity stored in the magnetic field. When that threshold is exceeded, the system seeks a lower energy state by expelling the flux rope. This expulsion is one way the Sun sheds excess magnetic helicity. As a CME propagates outward, it interacts with the solar wind and other structures, such as corrotating interaction regions. These interactions can deflect or decelerate the CME, altering its arrival time at Earth. In some cases, successive CMEs merge, forming a complex structure that can amplify geomagnetic effects. When multiple CMEs occur within a short period, the resulting disturbances in Earth's magnetosphere can last for days, creating extended periods of auroral activity. Understanding these interactions is an active area of research. The most immediate danger from a CME is the proton storm that often accompanies it. NOAA categorizes radiation storms from S1 to S5 based on the flux of greater than 10 mega-electron-volt protons measured by GOES satellites. An S1 storm occurs when the flux exceeds 10 particle flux units, while an S5 event exceeds 10 to the 5th units. These protons can damage satellite electronics, degrade solar panels, and pose a health risk to astronauts. On Earth, they can increase radiation exposure for passengers and crew flying over polar routes, prompting airlines to reroute flights during severe storms. Energetic protons are not the only particles accelerated during a flare. Electrons are also hurled into space and along closed loops, producing radio emission and high-energy X-rays. In the lower corona, the accelerated electrons heat plasma to tens of millions of Kelvin, emitting soft X-rays and extreme ultraviolet radiation. In the upper corona and interplanetary space, the electrons escape along open magnetic field lines and produce radio bursts that drift down in frequency as they travel outward. The combination of proton and electron beams makes each flare a rich laboratory for studying particle acceleration. Our atmosphere shields us from most high-energy radiation emitted by flares. The ozone layer absorbs much of the ultraviolet and soft X-ray flux, while the dense air scatters and attenuates harder radiation. However, these high-energy photons can ionize the upper atmosphere, particularly the ionospheric D region. The increased ionization enhances absorption of high-frequency radio waves, causing shortwave radio blackouts on the Sun facing side of Earth. These communication disruptions can last from minutes to hours, depending on the intensity of the flare. When the flux of high-energy protons is large enough, they penetrate Earth's magnetic field and collide with atmospheric molecules. These collisions produce additional secondary particles and ionization, further affecting radio communications and navigation systems. At the same time, the geomagnetic disturbances triggered by a CME can induce currents in power lines and pipelines. During severe storms, transformers and other electrical infrastructure can be damaged, leading to widespread blackouts. The famous Carrington event of 1859 is a reminder of what a truly large storm can do. Beyond the risks, the dance of particles and light also yields beauty. When energetic electrons spiral down magnetic field lines toward the poles, they collide with atoms and molecules in Earth's atmosphere. These collisions transfer energy to the atmospheric gases, which then re-emit that energy as light. Oxygen emits green and red light, while nitrogen produces blue and purple hues. The result is the aurora, a shimmering curtain of color that ripples across the polar skies, a visual reminder of our connection to the sun. Auroras form in regions called auroral ovals, which encircle the geomagnetic poles. They are aligned with magnetic field lines that connect Earth's atmosphere to space. During a solar storm, these ovals expand equatorward as more magnetic field lines are pushed earthward, increasing the number of particles that can enter the atmosphere. That is why intense storms allow auroras to be seen at much lower latitudes than usual. The colors and patterns vary with the energy of the particles and the composition of the atmosphere. In the thermosphere, where auroras occur, the air is thin and temperatures are high. Energetic particles deposit their energy into this tenuous gas, causing atoms to glow for seconds or minutes before the energy is lost. The height at which the glow occurs determines the color. Green emissions from oxygen are most common at 100 to 300 kilometers, while red emissions occur above 300 kilometers. Nitrogen emissions add subtle shades of blue and purple. Together, these emissions weave a tapestry of color that undulates in response to the changing flow of solar particles. The same processes that produce auroras on Earth occur on other planets with magnetic fields. Jupiter and Saturn have strong magnetospheres and are bombarded by plasma from their moons and the solar wind. Their auroras are far more powerful than those on Earth, glowing in ultraviolet and infrared wavelengths. On some days, the auroral power on Jupiter exceeds the total power consumption of civilization. Studying planetary auroras helps us understand magnetospheric physics across the solar system. While auroras are mesmerizing, solar storms can also produce less visible effects. The increased ionization in the ionosphere during a flare can delay or refract signals from global navigation satellites. Aircraft that rely on high-frequency radio communications may lose contact with ground stations when the D region absorbs radio waves. Low Earth orbit satellites encounter enhanced drag as the thermosphere warms and expands, causing them to lose altitude. All of these impacts are part of the subtle interplay between solar activity and our technological society. Ionizing radiation from solar flares includes X-rays and gamma rays. X-ray detectors aboard GOES satellites monitor this flux continuously, forming the basis for the classification of flares. Gamma rays, while rarer, offer insights into nuclear processes taking place in the solar atmosphere. The detection of gamma rays with specific energies can reveal the presence of certain isotopes, providing clues about the composition of the accelerated particles. Instruments such as RHESSI and the Fermi Gamma Ray Space Telescope have been crucial in this field. As electrons swirl around magnetic field lines, they radiate synchrotron and gyrosynchrotron emission. In the radio regime, this emission is observed as broadband continuum bursts. The spectrum and polarization of these bursts inform us about the energy distribution of electrons and the magnetic field strength. Observations show that the emission often originates from loops high in the corona, where the magnetic field is weaker. By modeling the emission, scientists infer the number of electrons and their distribution in energy. The interplay of light and particles continues long after the initial flare. As the magnetic field relaxes, a system of arcades forms above the flare site. These arcades consist of cooling loops that gradually shrink and descend, emitting soft X-rays and extreme ultraviolet radiation as they cool. The light from these post-flare loops can persist for hours or even days, marking the location of the eruption. Beneath the arcades, new magnetic flux may emerge, setting the stage for future activity. During large eruptions, energetic particles can even escape the sun's gravitational field and travel into interplanetary space. These particles, collectively known as solar cosmic rays, contribute to the background radiation that pervades our solar system. They are distinct from galactic cosmic rays, which originate from supernovae and other astrophysical sources. Solar cosmic rays can modulate the galactic cosmic ray flux, especially near the heliospheric current sheet. The balance between these particle populations varies with the solar cycle. On Earth, cosmic rays contribute to the ionization of the atmosphere and may influence cloud formation. During periods of high solar activity, increased solar modulation reduces the flux of galactic cosmic rays reaching Earth. Some researchers have proposed links between cosmic ray flux and climate, though these remain speculative. What is clear is that the sun's activity influences the space environment far beyond its surface. The birth of a solar flare is just one manifestation of this influence. The concept of the sun as a living star becomes apparent when we think of these processes as breathing. The magnetic fields rise and fall like lungs, filling with energy and expelling it in flares and CMEs. The corona acts as a membrane that bulges outward during eruptions and then contracts. The particles are like exhaled breaths, streaming into the solar system to be felt by planets and spacecraft. In this sense, a solar flare is a heartbeat, a momentary pulse that echoes across space. From the perspective of plasma physics, flares are natural laboratories. Conditions in the corona cannot be replicated on Earth. The combination of high temperature, low density, and strong magnetic fields is unique. By studying flares, scientists learn about fundamental processes such as magnetic reconnection, particle acceleration, shock formation, and turbulence. These processes occur in many astrophysical settings, from magnetospheres to accretion disks. Understanding them on the Sun therefore helps interpret observations throughout the universe. The Sun's proximity allows us to observe details that would be impossible elsewhere. Instruments like Solar Orbiter's Extreme Ultraviolet Imager and Parker Solar Probe's Fields instrument provide high-resolution measurements of magnetic fields, electric fields, and plasma densities. These data reveal small-scale structures, such as magnetic islands and current sheets, that play key roles in reconnection. They also show how waves propagate through the plasma, transporting energy away from the reconnection site. Such insights refine our models of flares. Another key aspect of flare physics is energy partition. When a flare occurs, some of the stored magnetic energy goes into heating plasma, some into accelerating particles, and some into driving bulk motions, like CMEs. Determining how the energy is divided among these channels helps us understand the efficiency of each process. Observations suggest that the fraction of energy given to accelerated electrons can be significant, sometimes comparable to the thermal energy. The interplay between these channels affects the subsequent evolution of the flare. Energy deposited in the chromosphere during the impulsive phase causes plasma to evaporate upward into the corona. This process, known as chromospheric evaporation, fills the flare loops with hot, dense plasma that emits soft X-rays and extreme ultraviolet radiation. Later, as the loops cool, the plasma condenses and drains back toward the chromosphere. High-resolution spectroscopic observations reveal upflows and downflows of plasma during these phases, providing clues about the energy transfer and heating mechanisms. These flows are part of the dynamical dance of a flare. Beyond the immediate vicinity of the flare, waves propagate through the solar atmosphere. These include magnetosonic waves, Alfvén waves, and shocks. Some of these waves can travel far into the corona, disturbing distant magnetic structures and possibly triggering secondary eruptions. On the solar surface, global waves known as Morton waves ripple across the chromosphere at speeds of hundreds of kilometers per second. In the corona, their counterparts are called EIT waves. Studying these waves provides insight into the large-scale response of the Sun to a flare. The Sun's influence does not end at the planets. The solar wind carries the imprint of solar activity to the heliopause, where it interacts with the interstellar medium. Changes in solar activity modulate the size and shape of the heliosphere, affecting how galactic cosmic rays are deflected. When the Sun produces a large number of CMEs, the cumulative effect can create a global disturbance known as a solar wind stream interaction region. This region can persist for weeks as it moves outward, influencing the environment encountered by spacecraft beyond Jupiter. From Earth's surface, we cannot see most of this drama directly. The Sun's light is so bright that subtle changes in the corona are overwhelmed. Yet by using specialized telescopes and satellites that view the Sun in ultraviolet, X-ray, and radio wavelengths, we can follow the birth and evolution of a flare. These observations are matched with models and simulations that translate the data into an understanding of the underlying physics. In this way, we piece together the story of each eruption, from its quiet beginnings to its explosive climax. Within the scientific community, solar flares are sometimes compared to earthquakes. Both involve the sudden release of stored energy through a rearrangement of structures. In one case, tectonic plates. In the other, magnetic fields. Both have foreshocks, main events, and aftershocks. And both can be described statistically by their frequency and magnitude. Flares follow a power law distribution, with small events being far more numerous than large ones. This means that while giant flares are rare, their cumulative contribution to energy release is significant. Watching the Sun is not only a scientific endeavor, but also a cultural one. For millennia, people have observed sunspots and eclipses, noting unusual events like great storms and auroras. In the 19th century, the Carrington event was recorded by both astronomers and telegraph operators. In the 20th century, radio engineers learned to cope with solar interference. Today, satellite operators and power grid managers track space weather with the same vigilance that mariners once watched the skies for storms. Our dependence on technology makes us more sensitive to solar whims. Understanding the birth of a solar flare has practical benefits. Accurate predictions could give astronauts time to seek shelter in spacecraft and airlines time to reroute flights. Power companies could brace for geomagnetically induced currents and protect transformers. Satellite operators could put sensitive instruments into safe mode. While precise forecasts remain elusive, improved observations and models offer hope that warnings can be issued hours to days in advance. The challenge is to interpret the subtle signs that herald an eruption. One promising approach is to analyze the magnetic topology of active regions. Certain configurations, such as delta-type sunspots, where opposite polarity umbrae share the same penumbra, are more prone to large flares. Photospheric vector magnetograms reveal the distribution of magnetic shear and helicity. Machine learning algorithms trained on past data can identify patterns associated with eruptive regions. Combining these data with real-time observations may enhance our ability to predict flares. However, the chaotic nature of magnetic reconnection means that surprises will always occur. The Sun's activity also influences the habitability of exoplanets around other stars. Young stars often produce flares much more energetic than our Sun's largest events. These superflares can strip away atmospheres and bombard planetary surfaces with high doses of radiation. By studying our own star, we learn about the environments that exoplanets might experience. This, in turn, informs our search for life in the universe. Understanding flares is therefore not just about protecting technology, but also about finding our place among the stars. As we continue to explore, we send spacecraft to sample the solar wind and measure magnetic fields. The Parker Solar Probe, launched in 2018, is diving closer to the Sun than any mission before, experiencing temperatures that would melt most metals. Its instruments are directly measuring the plasma and fields in the corona, flying through the zones where flares and CMEs originate. These measurements allow us to test theories of reconnection and particle acceleration under conditions impossible to create on Earth. Each perihelion brings it closer to the heart of solar activity. Solar Orbiter, launched in 2020, complements the Parker Solar Probe by taking high-resolution images and measuring the Sun's magnetic field from a unique orbit that gradually tilts out of the ecliptic. Together, these missions provide stereoscopic views of solar eruptions. They allow scientists to track CMEs from their birth to the point where they become part of the ambient solar wind. By comparing observations from multiple angles, researchers can reconstruct the three-dimensional structure of flares and CMEs. This synergy of missions is ushering in a golden age of heliophysics. While technology enables us to probe the Sun, the human experience of solar activity remains visceral. Seeing an aurora light up the night sky is a deeply moving experience. For many, it evokes a sense of wonder and connection to forces far beyond our daily lives. The same energy that can disrupt communications also paints the heavens with luminous arcs and curtains. In storytelling and mythology, auroras have been interpreted as spirits dancing, dragons breathing fire, or celestial battles. The science behind them does not diminish their magic. It adds a layer of appreciation for the physics that creates such beauty. At times, the sun's activity reminds us of our vulnerability. A strong geomagnetic storm could damage satellites, disrupt navigation, and even knock out power grids. Modern society depends on technologies that are susceptible to space weather. Yet, with careful monitoring and understanding, these risks can be mitigated. Rather than fear, we should feel respect and curiosity. The sun is not malevolent. It is a star following the laws of physics, and its storms are natural phenomena we can prepare for. Some of the earliest recorded flares were observed not by their light, but by their radio signatures. Amateur radio operators noticed sudden bursts of static that coincided with solar activity. During World War II, radar operators observed mysterious signals during certain times of day. These discoveries led to the realization that the sun was a powerful source of radio noise. Since then, radio astronomy has become a vital tool for studying the sun, revealing phenomena invisible in other wavelengths. In the radio domain, flares produce a bewildering variety of bursts. Type 1 storms consist of many short bursts that occur during active times and can last for days. Type 2 bursts drift from high to low frequencies over minutes and are thought to be produced by shock waves. Type 3 bursts are among the most common. They are brief and rapidly sweep downward in frequency, indicating electron beams moving outward along magnetic field lines. Type 4 bursts are broadband and can last for hours, occurring during the gradual phase of a flare. Type 5 bursts are rare and are thought to be extensions of Type 3 emission. The fact that radio bursts drift in frequency is a clue to their origin. As electron beams move through the corona, they encounter regions of decreasing plasma density. The emitted radio frequency is tied to the local plasma frequency, which decreases as density decreases. Therefore, the observed frequency drift corresponds to the outward motion of the electrons. By measuring the drift rate, scientists can estimate the speed of the electron beams. These speeds are typically a significant fraction of the speed of light. Flares also emit in infrared wavelengths. Infrared observations probe deeper layers of the atmosphere and can reveal the heating of the photosphere itself. These measurements complement ultraviolet and X-ray data, giving a more complete picture of the thermal structure of a flare. In addition, infrared lines can be used to measure magnetic fields through the Zeeman effect. This helps scientists map the changes in the photospheric magnetic field during the course of a flare. Such measurements are challenging, but provide critical information about energy release. Another fascinating aspect of flares is the production of neutrinos. During the most energetic flares, nuclear reactions can occur that produce neutrinos, ghostly particles that rarely interact with matter. Detecting solar flare neutrinos is extremely challenging because of the low flux and background noise. However, if detected, they would offer unique insights into the nuclear processes happening in the sun's atmosphere. This remains an area of active research and technological development, illustrating the many ways flares connect disciplines. The sun's corona is threaded by a complex web of magnetic field lines. During reconnection, some of these lines become open, allowing particles to escape, while others close, trapping particles in loops. This restructuring changes the connectivity of the magnetic field throughout the corona. Field lines that were previously connected to Earth may become attached to other regions, altering the path of the solar wind. These changes can have subtle effects on the flow of energy and particles throughout the heliosphere. From the smallest microflare to the largest X-class event, all flares follow the same basic principles. They involve the storage of magnetic energy, the sudden reconfiguration of field lines, and the acceleration of particles. The scale varies, but the underlying physics is universal. This universality allows us to apply insights from solar flares to other astrophysical phenomena, such as magnetoflares and accretion disk eruptions. The Sun thus serves as a Rosetta Stone for high-energy astrophysics, translating complex physics into an accessible language. Cosmic magnetism is a pervasive force. In galaxies, magnetic fields influence the formation of stars and the dynamics of interstellar clouds. In clusters of galaxies, magnetic turbulence shapes the distribution of hot gas. The reconnection processes that power solar flares also occur in these environments, albeit on vastly different scales. By understanding reconnection on the Sun, we gain insight into phenomena like cosmic rays, jets from black holes, and even the dynamics of the early universe. At the heart of magnetic reconnection is the breaking of the frozen in condition. In ideal magnetohydrodynamics, field lines move with the plasma and cannot cross. Reconnection requires a breakdown of this ideal behavior, allowing field lines to diffuse through the plasma. This diffusion can be facilitated by processes like anomalous resistivity, turbulence, or kinetic effects. Understanding how these mechanisms operate in the corona is crucial for explaining the fast reconnection rates observed. Recent observations suggest that turbulence plays a significant role in accelerating reconnection. Flares also shed light on the heating of the corona itself. For decades, scientists have wondered why the corona is millions of degrees hotter than the surface beneath it. One hypothesis is that countless tiny reconnection events, or nanoflares, release small amounts of energy that collectively heat the corona. Although each event is too small to observe directly, their cumulative effect could maintain the high coronal temperature. Studying flares across the energy spectrum helps test this hypothesis and refine models of coronal heating. In addition to particle acceleration, reconnection accelerates bulk plasma flows. These flows can manifest as jets or plasmoids that propagate away from the reconnection region. In the corona, such jets can be seen as narrow, bright features that shoot outward from flare sites. In some cases, jets trigger secondary flares as they interact with distant magnetic structures. Observing and modeling these flows provides insight into how reconnection redistributes mass and energy. Solar flares have inspired countless analogies, yet none capture the full richness of their dynamics. They are explosions, yet they are also reorganizations. They are bright flashes, yet they leave behind long-lasting afterglows. They are local events, yet they influence the entire heliosphere. This combination of immediacy and endurance is part of what makes flares so fascinating. To understand them is to glimpse the interplay between order and chaos in a magnetic universe. While we study the Sun with advanced technology, we are also participants in its dance. Every heartbeat of the Sun sends ripples through space that eventually touch our planet. The light that warms our days and powers life on Earth is the gentle side of this star. The flares and storms are its more dramatic expressions. Recognizing this duality deepens our appreciation of the Sun. It is both familiar and extraordinary, both constant and unpredictable. As the 19th century gave way to the 20th, scientists began to correlate sunspot numbers with terrestrial phenomena. They noticed that auroral activity increased during periods of high sunspot counts. Radio operators learned to expect interference when large sunspot groups were visible. Meteorologists speculated about links between solar activity and weather patterns, though such connections remain controversial. The birth of a solar flare thus became more than an astronomical curiosity. It became a subject of interdisciplinary study. In recent decades, our capacity to observe the Sun has grown tremendously. Space-based observatories provide continuous coverage across multiple wavelengths, while ground-based telescopes like the Daniel K. Inouye Solar Telescope deliver unprecedented spatial resolution. Computers simulate flares with millions of elements, capturing details of magnetic structure and plasma flow. At the same time, citizen scientists and amateurs contribute by monitoring sunspot numbers and capturing images of auroras. This democratization of solar science brings more eyes to the task of understanding our star. International collaboration is vital in heliophysics. Space weather affects all nations, and the data needed to study the Sun come from spacecraft launched by multiple space agencies. Instruments must be cross-calibrated, and data must be shared quickly during events. Organizations like the International Space Environment Service coordinate these efforts, ensuring that forecasters around the world have the information they need. This global cooperation reflects the global impact of the Sun's activity. Our understanding of flares is also shaped by theoretical advances. Mathematical models of magnetohydrodynamics describe how magnetic fields evolve in a conducting fluid. Numerical simulations solve these equations under conditions similar to the solar corona. These simulations reveal the formation of current sheets, the onset of tearing instabilities, and the formation of magnetic islands, all precursors to reconnection. Comparing simulation results with observations helps validate theories and identify missing physics. The interplay between theory and observation drives the field forward. One of the ongoing challenges is to explain the variety of flare morphologies. Some flares are compact and confined, releasing energy in a localized region, while others are eruptive, launching CMES. The difference likely depends on the magnetic connectivity of the active region and the presence of overlying field lines that either confine or allow escape. Determining the conditions that lead to each type remains an active area of research. This challenge underscores the complexity of solar magnetic fields. On the observational front, measuring magnetic fields in the corona is difficult. Direct measurements are possible in the photosphere, but in the corona, the plasma is too tenuous and the Zeeman splitting too small. Scientists infer coronal fields by extrapolating photospheric measurements using force-free models. They also use radio and infrared observations to estimate field strengths. Future missions may carry instrumentation capable of measuring the coronal magnetic field directly. Such advances would revolutionize our understanding of flares and CMES. Beyond the scientific community, educating the public about solar flares and space weather is essential. Understanding that the Sun influences technologies like GPS, radio communications, and power grids helps people appreciate the need for monitoring. It also inspires curiosity about the cosmos. Programs like NASA's Radio Jove let students build radio telescopes to listen to solar and planetary radio emissions. Planetariums and science centers offer shows about the Sun's activity. These outreach efforts ensure that the beauty and science of solar phenomena reach a broad audience. Looking ahead, new technologies promise to enhance our ability to monitor and predict flares. Artificial intelligence algorithms can scan vast datasets for signs of impending activity. CubeSats and small satellites can be deployed in swarms to provide multi-point measurements of the solar wind. Ground-based magnetometers can detect subtle changes in Earth's field that herald incoming storms. As our understanding deepens, we may eventually forecast solar flares with the same confidence that we forecast hurricanes. Such progress will be a testament to human ingenuity and our connection to the star that sustains us. The story of a solar flare is a story of energy waiting to be released. It begins with magnetic fields twisted by the Sun's rotation and convective motions. It builds as these fields store energy in invisible knots and loops. It reaches a climax when reconnection unties the knots unleashing beams of particles and cascades of light. And it continues as the light and particles travel through space, interacting with planets, atmospheres, and magnetic fields. By following this story, we honor the intricate dance that connects us to our star. Deep beneath the sun's surface, acoustic waves reverberate through its interior. Helioseismology uses these waves to map flows and rotation below the photosphere. Measurements reveal bands of faster and slower rotation, and these flows influence the magnetic field that emerges at the surface. By listening to the sun's internal vibrations, scientists infer the subsurface dynamics that give rise to active regions. This knowledge complements surface observations, providing a more complete picture of how magnetic stress is generated. The 11-year solar cycle modulates the number of sunspots and flares. During solar maximum, dozens of sunspots may be visible at once, and flares occur daily. During solar minimum, the sun's surface can be almost featureless, with only occasional small spots. The cycle arises from the slow reversal of the sun's global magnetic field, a process driven by the differential rotation of the outer layers. Each cycle has its own rhythm, with some maxima being stronger than others. Within the classification system, even the largest flares vary in duration and complexity. A compact flare may release its energy in a matter of minutes, while a long-duration flare associated with a CME can last for hours. The light curves recorded by satellites show distinct phases: a rapid rise during the impulsive phase, followed by a gradual decline as the plasma cools. The shape of the light curve and the timing of emissions at different wavelengths offer clues about the physical processes at work. Comparing these curves between events helps researchers identify patterns. Ground-based observatories contribute to flare research by observing the sun in hydrogen alpha light. The chromosphere, where flares manifest as bright ribbons, emits strongly at this wavelength. Solar telescopes with narrowband filters can track the evolution of these ribbons in real time. Spectrographs measure Doppler shifts that reveal motions of plasma toward or away from the observer. Together with space-based data, these observations enrich our understanding of the flare phenomenon. Earth's magnetosphere has a distinct structure that determines how it responds to solar storms. The day-side magnetopause is compressed by the solar wind, while the night side stretches into a long magnetotail. When a CME strikes, magnetic reconnection in the magnetotail can release energy stored in Earth's field, injecting particles into the inner magnetosphere. These injections power the bright auroras that cascade over polar regions. Thus, both solar and terrestrial magnetic reconnection contribute to space weather. Scientists categorize geomagnetic storms using the KP index, which measures disturbances in Earth's magnetic field. A storm rated KP5 is considered moderate, while KP8 or 9 indicates extreme activity. These ratings correlate with the strength of auroras and the potential impact on power systems. Like the flare classification, the KP scale helps communicate the severity of space weather to stakeholders. Forecasting models combine solar observations, CME propagation estimates, and magnetospheric models to predict KP values. Our moon lacks a significant atmosphere and magnetic field, so it receives the full brunt of solar radiation. During a powerful flare or radiation storm, the moon's surface is bombarded by high-energy particles. Future lunar explorers will need to consider this hazard and plan activities around space weather forecasts. Martian astronauts face similar challenges, as Mars has a thin atmosphere and a patchy crustal magnetic field. Understanding solar storms is therefore essential for human exploration beyond Earth's protective magnetosphere. Mercury, being closest to the Sun, experiences particularly intense space weather. The planet has a weak magnetic field that barely deflects solar particles. Flares and CMEs batter its surface, sputtering material into space and contributing to a tenuous exosphere. Measurements by the MESSENGER spacecraft revealed that Mercury's magnetosphere is highly dynamic, responding quickly to changes in solar activity. Studying Mercury helps us understand space weather in extreme environments. Solar superflares observed on other stars dwarf anything our Sun produces. These events can be tens of thousands of times more energetic than the largest solar flares. Astronomers detect them by monitoring the brightness of stars over time. The existence of superflares raises questions about the potential impact on exoplanets. It also prompts scientists to ask whether the Sun might produce such an event in the future. Current evidence suggests that superflares are more common on younger, rapidly rotating stars. Historical records from East Asia describe unusual sightings of red and white vapors in the sky. These descriptions are now thought to refer to auroras seen at low latitudes during strong geomagnetic storms. By combining such records with sunspot observations and radioisotope data from tree rings, scientists reconstruct the history of solar activity. These reconstructions show that the Sun has experienced periods of both high and low activity over centuries. They provide context for modern observations and help us assess long-term trends. During strong solar storms, cosmic rays reaching Earth can decrease temporarily. This phenomenon, known as a Forbush decrease, occurs when a CME sweeps away galactic cosmic rays in its path. As the interplanetary magnetic field strengthens, it acts as a shield against high-energy particles from outside the solar system. Ground-based neutron monitors detect the reduction in cosmic ray intensity, providing yet another tool for studying solar eruptions. Forbush decreases illustrate the interconnectedness of solar and galactic particles. Flares influence Earth's upper atmosphere in other ways. Enhanced ultraviolet and X-ray radiation heat the thermosphere, causing it to expand. This increased density at higher altitudes leads to greater drag on satellites, potentially altering their orbits. Operators of low Earth orbit satellites monitor solar activity closely to plan orbital adjustments. Flares can also increase the ionization in the E and F regions of the ionosphere, affecting radio propagation at medium and high frequencies. Navigation systems like GPS rely on signals that traverse the ionosphere. Changes in electron density during a flare or radiation storm can delay these signals, introducing errors in position estimates. Modern receivers use dual frequencies to correct for ionospheric delays, but severe storms can still degrade accuracy. Aviation systems that depend on satellite navigation must be aware of these potential disruptions. Space weather awareness is therefore crucial for maintaining the reliability of positioning services. The study of flares has fostered collaboration between astronomers and plasma physicists. The plasma conditions in the solar corona present a natural laboratory for testing theories of collisionless plasmas. Research on magnetic reconnection in flares informs understanding of reconnection in laboratory devices such as tokamaks, which aim to achieve controlled nuclear fusion. Conversely, laboratory experiments provide insights that can be applied to solar observations. This synergy accelerates progress in both fields. Computational models of flares require solving complex sets of equations. These models include magnetohydrodynamic equations for the plasma, kinetic equations for particle distributions, and radiative transfer equations for the emitted light. High-performance computing allows scientists to simulate flares in 3 dimensions, capturing the emergence of magnetic fields, the onset of reconnection, and the acceleration of particles. Comparing these simulations with observations helps refine the models and identify key parameters. As computing power grows, simulations will become even more realistic. On a human level, the unpredictability of solar flares offers a lesson in humility. We can model and forecast to the best of our ability, yet there will always be surprises. This uncertainty reminds us that nature operates on its own terms. Rather than seeking absolute control, we must adapt to variability. In doing so, we strengthen our resilience and deepen our respect for the forces that shape our environment. Auroras have long inspired art and literature. Indigenous cultures in the Arctic region have stories about spirits dancing or ancestors communicating through the lights. Early European explorers wrote about streamers and curtains in their journals, struggling to describe their movement. Modern photographers capture time-lapse images that reveal patterns and structures not visible to the naked eye. Each representation, whether myth or photograph, conveys a sense of awe at the interplay between solar particles and Earth's atmosphere. Space weather awareness is growing in the public sphere. News outlets now report on major solar events, and some smartphone apps provide space weather forecasts. These reports help people understand unusual events, like intense auroras seen at low latitudes. They also encourage interest in astronomy and space science. As our society becomes more reliant on technology, awareness of the sun's activity will only become more important. The journey of a proton accelerated during a flare is remarkable. In a fraction of a second, it goes from being part of the solar plasma to traveling at nearly the speed of light. It then traverses the 93 million miles to Earth in less than an hour, spiraling along interplanetary magnetic field lines. Upon reaching Earth, it may collide with the atmosphere, generating cascades of secondary particles. This journey illustrates the direct connection between events on the Sun and particles in our skies. Electrons accelerated during a flare follow similar paths, but produce different signals. Their smaller mass allows them to achieve higher velocities, though their trajectories are more easily deflected by magnetic fields. These electrons produce radio emissions and X-rays as they decelerate in the solar atmosphere. When they reach Earth, they can contribute to auroral emissions. Studying the spectra of these electrons helps determine the mechanisms that accelerated them in the first place. Radiation storms are categorized not only by proton flux, but also by their potential to harm biological tissue. At high intensities, energetic protons can damage cellular DNA. Space agencies monitor solar radiation closely during crewed missions, and spacecraft are designed with shielding to reduce exposure. Astronauts may retreat to more shielded areas during storms. In the future, missions to the Moon and Mars will require careful planning to avoid periods of heightened solar activity. Though Earth's magnetosphere protects the surface from most solar radiation, it does not eliminate all effects. High-altitude flights, particularly near the poles, expose passengers and crew to increased radiation during solar storms. While the doses are typically below regulatory limits, flight crews who spend many hours at high altitude accumulate exposure over time. Awareness of solar activity helps airlines manage this risk by adjusting flight paths when necessary. Power grids are vulnerable to geomagnetically induced currents during severe space weather. When the magnetosphere is disturbed, electric currents are induced in the ground and in long conductors like power lines. These currents can overload transformers and cause voltage swings. Utilities monitor geomagnetic activity and may take preventative measures, such as reducing load or isolating equipment. The costs of mitigation are justified by the potential costs of a widespread blackout. Understanding solar flares thus contributes to the reliability of our electrical infrastructure. Satellites in geostationary orbit are particularly exposed to space weather. They rely on electronics that can be damaged by energetic particles. Solar storms can cause single-event upsets, momentary glitches, or permanent failures. Operators may place satellites in safe mode during intense events to protect sensitive components. Designing robust satellites requires understanding the radiation environment and planning for worst-case scenarios. The synergy between solar physics and engineering ensures that we can maintain our space-based capabilities. The magnetosphere of Earth includes several radiation belts, known as the Van Allen belts, composed of trapped electrons and protons. During storms, these belts can be energized by incoming particles. This energization increases the flux of high-energy electrons, which pose a hazard to satellites passing through the belts. Understanding how flares and CMEs affect the belts is part of the broader field of magnetospheric physics. Monitoring satellites provide data to track changes in the belts, aiding both science and operations. The magnetosphere also has an extended plasma region, called the plasmasphere, which co-rotates with Earth. During geomagnetic storms, the plasmasphere can be eroded, its outer layers stripped away. This erosion changes the propagation of radio waves in the magnetosphere, affecting communications. The replenishment of the plasmasphere after a storm is a slow process, taking days to weeks. This dynamic adds yet another layer to the complex response of Earth's environment to solar activity. The impact of solar activity is not limited to Earth. Mars experiences auroras across its entire atmosphere because it lacks a global magnetic field. Instead, localized crustal fields create patchy magnetic umbrellas that concentrate the auroral emissions. The MAVEN spacecraft has observed these diffuse auroras, which occur when solar energetic particles interact with the upper atmosphere. These observations help us understand the long-term loss of Martian atmosphere to space and provide context for planetary habitability. Venus, without a significant magnetic field, interacts with the solar wind in a different way. The solar wind directly impacts its upper atmosphere, creating a bow shock and a long magnetotail formed by induced currents. Energetic particles and radiation from flares and CMEs can erode Venus's atmosphere, though its dense atmosphere and thick cloud cover provide some protection. Studying these interactions helps us understand atmospheric evolution on terrestrial planets. Even the gas giants feel the effects of solar activity, though they have strong magnetic fields of their own. Jupiter's immense magnetosphere is shaped by particles from its volcanic moon Io. Solar flares and CMEs can compress this magnetosphere, triggering bright auroras at Jupiter's poles. The Hubble Space Telescope has captured ultraviolet images of these auroras, revealing their response to solar storms. This demonstrates that the Sun's influence extends throughout the solar system. The Sun's magnetic field also extends beyond the planets, forming a vast bubble known as the heliosphere. The heliosphere acts as a shield against interstellar cosmic rays. Solar flares and CMEs contribute to the turbulence and structure within this bubble. As the solar cycle waxes and wanes, the size and strength of the heliosphere change. When the Sun is active, the enhanced solar wind can cause the heliosphere to expand. Conversely, during quiet times, it may contract, allowing more cosmic rays to enter the inner solar system. One of the ways we observe the heliosphere is by measuring the flux of galactic cosmic rays. When solar activity is high, the increased solar wind and magnetic turbulence scatter cosmic rays, reducing their intensity at Earth. Conversely, during solar minimum, cosmic ray intensity increases. This modulation is important for space travel and for our understanding of cosmic ray origins. The interplay between solar and cosmic radiation is yet another example of the Sun's influence beyond its immediate vicinity. The outer boundary of the heliosphere, the heliopause, marks the point where the solar wind pressure balances the interstellar medium. Voyager 1 and Voyager 2 have crossed this boundary, providing in situ measurements. These spacecraft recorded changes in particle populations and magnetic fields as they exited the heliosphere. Solar activity influences conditions at the heliopause, sending shocks and disturbances that propagate to the edge of the solar system. Thus, the birth of a solar flare can send ripples that are felt billions of miles away. Solar flares are sometimes accompanied by jets of material called surge events. Surges occur when cool chromospheric plasma is ejected along magnetic field lines. These surges can reach heights of tens of thousands of kilometers before falling back toward the surface. They are often seen in association with filament eruptions. Studying surges provides insights into the mass motion and energy balance during flares. Another related phenomenon is the flare spray. Streams of plasma that shoot outward during a flare but do not become full CMEs. Flare sprays carry less mass than CMES but can still reach impressive speeds. They may represent an intermediate stage between confined flares and full eruptions. Observations of sprays help clarify the conditions that determine whether an eruption will remain confined or will escape into space. The variety of eruptive phenomena demonstrates the complexity of magnetic energy release. The relationship between flares and sunspot magnetic complexity has led to classification schemes for sunspots. The Mount Wilson classification categorizes sunspot groups into alpha, beta, gamma, and delta types based on the number and arrangement of polarity regions. The most complex, delta, contains umbrae of opposite polarity within the same penumbra and is associated with large flares. Monitoring sunspot classification helps forecasters assess flare risk. Combined with measurements of magnetic shear, it offers a window into the buildup of magnetic stress. Solar flare prediction remains a formidable challenge. Even with comprehensive data, the system is inherently chaotic. Small changes in the magnetic environment can make the difference between a quiet day and a large eruption. Researchers continue to explore statistical and machine learning methods to extract meaningful patterns. While these methods improve probabilistic forecasts, they cannot predict the exact timing or magnitude of a flare. Accepting uncertainty is part of working with complex natural systems. The global network of space weather monitoring includes satellites such as the Deep Space Climate Observatory, DSCOVR, which sits at L1 and measures the solar wind before it reaches Earth. DSCOVR provides lead time of about 15 to 60 minutes for incoming CMEs. Combined with ground-based magnetometers and all-sky images, these instruments give forecasters a comprehensive view of conditions. When data indicate a storm is imminent, alerts are issued to industry and government agencies. This collaboration mitigates the impact of space weather on critical infrastructure. Auroral substorms are localized disturbances that occur when energy stored in Earth's magnetotail is suddenly released. They manifest as brightening and rapid motion of auroral arcs. Substorms are triggered by reconnection in the tail and can occur multiple times during a geomagnetic storm. Although not directly caused by solar flares, they are part of the chain of events initiated by solar activity. The study of substorms bridges solar and magnetospheric physics. Radiation storms can also affect the atmosphere's chemistry. Energetic particles penetrating the polar regions produce odd nitrogen and odd hydrogen species that catalyze ozone destruction. During very strong events, minor reductions in stratospheric ozone have been observed. These changes are temporary, but highlight another pathway by which solar activity can influence Earth's environment. Long-term monitoring of atmospheric composition helps assess the cumulative impact of these events. Commercial companies are increasingly taking interest in space weather. Satellite operators, airlines, and power utilities have begun to integrate space weather data into their operations. Insurance companies assess risks associated with geomagnetic storms when covering satellites and power infrastructure. The emerging private spaceflight industry also considers radiation exposure for tourists and crew. As our economy expands into space, the importance of space weather awareness will grow accordingly. Educational initiatives encourage students to engage with space weather. Programs like the Global Oscillation Network Group allow students to monitor the sun's oscillations and contribute data. Amateur radio enthusiasts participate in citizen science by listening for solar radio bursts. These activities not only enrich science education, but also build a culture of observation and curiosity. They show that anyone can contribute to our understanding of the sun. In the field of astrophysics, understanding flares on the sun helps interpret flares on other objects. For instance, magnetars, neutron stars with extremely strong magnetic fields, produce giant flares that release more energy in a fraction of a second than the sun does in a century. Though the conditions are extreme, some of the same physical principles apply: magnetic reconnection and particle acceleration. By comparing these systems, scientists gain insights into the universal laws governing magnetic explosions. Accretion disks around black holes and young stars also experience magnetic reconnection events. These events can produce X-ray flares and jets, similar in some ways to solar flares and CMEs. In these settings, the magnetic fields are anchored in the disk material rather than a solid surface. Flares in accretion disks influence the flow of gas onto the central object and can affect the formation of planets in protostellar disks. Once again, the sun serves as a nearby example of processes that operate throughout the cosmos. Cosmic weather is not limited to the electromagnetic domain. Gravitational waves produced by astrophysical events also propagate through space, carrying information about their sources. Though solar flares do not generate detectable gravitational waves, the same dynamic interplay of fields and particles that we see in flares is mirrored in other phenomena. The universe is a tapestry woven from energy, matter, and spacetime. Each thread influences the others, creating patterns that repeat across scales. Throughout history, the sun has been revered as a symbol of constancy. It rises and sets with regularity, providing light and warmth that sustains life. Yet, within its constancy lies variability. The cycles of activity remind us that even seemingly stable systems can harbour dynamic processes. Recognizing this duality enriches our relationship with the sun, prompting both reverence and inquiry. The study of flares exemplifies this balance of awe and curiosity. In many cultures, solar eclipses were feared as signs of disruption. Today, we understand that an eclipse offers a rare opportunity to see the corona and observe structures that are otherwise hidden. During the totality, coronal streamers, prominences, and sometimes even flares become visible. These observations have historically provided insights into coronal structures and remain valuable today. The next time a total solar eclipse occurs, observers may witness the early stages of a flare or even a CME launching into space. Time itself feels different on the sun. Processes that take seconds for us unfold over minutes or hours there, while other processes span decades or centuries. The build-up of magnetic stress is slow, yet the release is sudden. The radiation travels to us almost instantaneously, while the particles take minutes to hours. Understanding these timescales is essential for interpreting observations and planning responses. The sun teaches us to think across a broad range of temporal rhythms. The composition of the solar atmosphere influences the radiation produced during flares. Elements like iron, calcium, and magnesium emit characteristic spectral lines when ionized. Observing these lines allows scientists to measure temperatures, densities, and flows within the flare. Each line originates from a specific transition and thus traces particular layers of the atmosphere. The rich spectra recorded during flares are like fingerprints, revealing details of the plasma environment. During a flare, the spectra can change rapidly. Lines broaden and shift due to Doppler motions, and new lines appear as the plasma heats to higher ionization states. Monitoring these changes requires instruments that can take rapid, high-resolution spectra. Advances in detector technology and instrumentation have made such observations possible. Combining spectroscopic data with imaging provides a comprehensive view of the flare's evolution. This synthesis of data is essential for unraveling the complexity of flares. Particle detectors aboard spacecraft such as ACE, STEREO, and SOHO record the arrival of energetic particles from flares. These instruments measure the energy and composition of the particles, revealing information about their source. For example, an abundance of helium-3 indicates a process called stochastic acceleration. By comparing particle data with electromagnetic observations, scientists piece together the sequence of events during a flare. This multi-messenger approach is critical for a full understanding. The correlation between solar activity and climate remains an area of active study. While the sun's irradiance varies slightly over the solar cycle, these variations alone cannot explain recent climate change. However, changes in ultraviolet output can influence the stratosphere and, through complex feedbacks, may impact weather patterns. Understanding these subtle influences requires careful analysis and long-term datasets. The interplay between solar variability and climate underscores the importance of studying the sun from multiple perspectives. In the early 20th century, Norwegian scientist Christian Birkeland proposed that auroras were caused by currents flowing along magnetic field lines. His experiments with terrella, small magnetized spheres, reproduced auroral patterns in the laboratory. Today, the concept of field-aligned currents is well established, and satellites measure these currents flowing into and out of the polar regions. Birkeland's pioneering work laid the foundation for modern space physics. His legacy reminds us that creative experimentation can yield profound insights. The names of prominent solar flares sometimes reflect their impacts. The Carrington event of 1859 was named after the astronomer Richard Carrington, who observed the flare that caused telegraph fires. Other notable events include the Bastille Day flare of 2000 and the Halloween storms of 2003. These names help the public remember space weather events and their effects. They also serve as benchmarks for comparing future events. Each new flare adds to the growing catalogue of solar activity. Space weather forecasting is a multidisciplinary effort that includes observational astronomy, data analysis, physics, and engineering. Specialists analyze satellite data, run numerical models, and interpret results for end users. Communication channels ensure that alerts reach those who need to know, from satellite operators to aviation authorities. This system is akin to terrestrial weather forecasting, but with unique challenges. The intangible nature of the phenomena and the vast distances involved require specialized expertise. The field of heliophysics extends beyond the sun to include the influence of solar activity on the entire solar system. It encompasses the study of planetary magnetospheres, the solar wind, and the heliosphere. Researchers in this field collaborate with planetary scientists, astrophysicists, and atmospheric chemists. This interdisciplinary approach enriches our understanding of the sun's role as the central engine of our cosmic neighborhood. Each solar flare is a small piece of a larger puzzle. In classrooms around the world, teachers use images and data from solar observatories to inspire students. Lessons about sunspots, flares, and auroras connect physics, astronomy, and earth science. Students learn that the sun is not just a distant object, but a dynamic star that influences their daily lives. Hands-on activities, such as building a simple radio telescope or modeling magnetic fields with iron filings, bring the subject to life. Engaging the next generation ensures the continued study and appreciation of solar physics. Artistic representations of flares often capture the grandeur of the phenomenon. Painters depict arcs of glowing plasma and swirling fields, sometimes exaggerating colors for dramatic effect. Musicians compose pieces inspired by the rhythm and power of solar storms. Poets find metaphor in the sudden release of energy after long tension. These creative works remind us that science and art are complementary ways of understanding and expressing our relationship with nature. As we gaze at the sun through special glasses during a solar eclipse, we might reflect on the hidden activity beyond the visible disk. Beneath the surface, magnetic fields twist. Above it, the corona shimmers and flows. Somewhere, loops are coiling and preparing to snap. The calm face we see belies a complexity that only becomes apparent when we look with the right instruments. Awareness of this hidden world adds depth to even simple observations. Human history has been shaped by the sun's regular cycles. Agricultural calendars depend on the seasons, and solar calendars mark the passage of years. Yet, beyond this regularity, sporadic solar storms have also had an impact. Telegraph systems, radio communications, and power grids have all been affected by flares. As we become more interconnected, our vulnerability to solar activity increases, making its study all the more relevant. The birth of a solar flare is also a story of resilience. Life on Earth has evolved under the influence of solar radiation. The atmosphere and magnetosphere have developed to shield organisms from harmful particles and photons. Even as the sun occasionally lashes out with powerful flares, the Earth's systems adapt and recover. This resilience is a testament to the robustness of our planet and the life it harbours. It provides hope as we face other environmental challenges. Philosophically, flares invite contemplation of energy and impermanence. Energy stored in magnetic fields eventually dissipates. Nothing remains static. The transformation from potential to kinetic, from order to chaos, echoes processes throughout nature. Recognizing these patterns can influence how we think about change in our own lives. In this way, solar physics offers both scientific insights and metaphors for personal growth. At the frontier of solar research, scientists are exploring the possibility of detecting pre-flare signatures in the corona. These signatures might include subtle changes in magnetic topology, flows, or plasma heating. Instruments with high cadence and sensitivity are needed to capture these transient signals. If such precursors can be identified reliably, they could improve flare forecasts. This research represents the cutting edge of prediction efforts. Long-term monitoring has revealed that the sun experiences prolonged periods of low activity, known as grand minima. The Maunder minimum of the 17th century is the most famous example. During this period, very few sunspots were observed, and auroras were rare. Proxy data suggests that the sun's output may have been lower than usual. Understanding these minima helps scientists assess the range of solar variability and its potential impacts on Earth's climate and space environment. Conversely, there may have been periods of exceptionally high solar activity, though evidence is sparse. These grand maxima could involve more frequent or more intense flares and CMEs. Tree ring data and ice core records containing isotopes like carbon-14 and beryllium-10 offer clues. By studying these records, researchers seek to reconstruct the Sun's activity over millennia. This context can inform our understanding of present-day events and help assess long-term risks. Solar analogues, stars similar to the Sun in mass and temperature, provide additional perspective. Observations of these stars reveal a range of flare behaviors. Some have cycles similar to the Sun's, while others show irregular activity. By comparing the Sun to its stellar siblings, astronomers refine models of stellar dynamos and magnetic activity. This comparative approach helps place our Sun within the broader stellar population and underscores the diversity of magnetic phenomena. Ultimately, the study of solar flares is a journey of discovery that spans disciplines and connects people around the world. It marries cutting-edge technology with ancient curiosity. It reveals the power of invisible forces and the beauty of visible light. It reminds us that we are part of a cosmic environment shaped by fields and particles moving according to fundamental laws. As our understanding grows, so too does our capacity to live in harmony with the star that sustains us. The birth of each solar flare is like a chapter in an ongoing epic. Though one eruption ends, the forces that created it continue to operate, twisting fields and moving plasma. New active regions rotate into view, each with its own potential for drama. The energy released into space travels far beyond Earth, shaping environments around distant planets and spacecraft. In this way, the story of a flare does not end on the Sun. It reverberates throughout the solar system and beyond. As we leave this exploration of a flare's genesis, we turn our attention to what comes after. The particles and waves unleashed by the Sun must navigate the interplanetary medium, encountering magnetic fields, planets, and cosmic rays. Their interactions produce phenomena that are as varied as they are mesmerizing. The next stage of our journey will follow these travelers, tracing their paths from the Sun's fiery surface to the farthest reaches of the heliosphere. The voyage continues, and the cosmic storm unfolds in the space between stars. At the outer boundary of the magnetosphere lies the magnetopause, a dynamic frontier where solar wind plasma and Earth's magnetic field meet. Here, magnetic reconnection can occur, linking solar and terrestrial field lines and allowing energy and particles to transfer into the magnetosphere. Kelvin-Helmholtz instabilities can ripple along the boundary as shear flows between the shocked solar wind and magnetospheric plasma generate waves that roll and mix. These processes are fundamental to the transport of energy and mass into the magnetosphere and illustrate how fluid the boundary between worlds can be. Just outside the magnetopause, the solar wind is slowed and heated at a shockwave called the bow shock. This shock forms because the supersonic flow must divert around Earth's magnetic obstacle, compressing and deflecting the plasma. Downstream of the shock lies the magnetosheath, a turbulent region where the shocked flow drapes around the magnetosphere, full of fluctuations and eddies. Conditions in the magnetosheath control how much energy and momentum reach the magnetopause and thus influence geomagnetic storms. The global electric circuit links the ionosphere and the surface through thunderstorms and fair weather currents. Space weather can alter the ionospheric potential difference, modulating this circuit and influencing atmospheric electricity. Enhanced fluxes of energetic particles can change the conductivity of the upper atmosphere, potentially affecting lightning rates and the formation of sprites and other transient luminous events. researchers explore how cosmic and solar influences interplay with terrestrial weather and climate in this subtle electrical web. Many animals navigate using Earth's magnetic field. Migratory birds sense the inclination and strength of the field to orient during long journeys. Sea turtles use magnetic signatures to return to nesting beaches after years at sea, and some whales may use magnetic cues during migrations. Space weather disturbances can alter the field temporarily, and there are anecdotal reports of navigation errors coinciding with storms. Studying magnetoreception in animals offers another window into our planet's intimate connection with space. Radiation exposure from cosmic rays and solar particles is a concern for aviation and space travel. At cruising altitude, passengers and crew are exposed to higher levels of ionizing radiation than at the surface, with doses increasing toward the poles and during solar particle events. Airlines adjust flight paths to minimize exposure during major storms and monitor forecasts to protect pregnant crews and frequent flyers. Long-term human missions beyond low Earth orbit must contend with even higher doses, making radiation shielding and forecasting essential for astronaut health. The Van Allen radiation belts encircle Earth like invisible rings, populated by high-energy electrons and protons. These belts wax and wane in response to solar activity, and during storms, they can swell with energetic particles that pose risks to spacecraft electronics and human spaceflight. Missions such as the Van Allen probes have provided detailed measurements of belt dynamics, revealing how waves accelerate and scatter particles. Designing satellites to withstand or avoid these belts is a key aspect of mission planning and highlights the complexity of near-Earth space. The Moon, lacking a global magnetic field, is directly exposed to the solar wind, except when it passes through Earth's magnetotail. During these passages, lunar orbiters observe changes in plasma environments and charging of the surface. Charged particles can build up electric fields that loft dust above the lunar regolith, creating a tenuous exosphere. Understanding how space weather affects the Moon informs plans for long-term human presence and protects instruments that will operate on its surface and in orbit. Monitoring the Sun and interplanetary space requires an armada of spacecraft placed at strategic locations. At the first Lagrange point, satellites like SOHO, ACE, and DSCOVR provide continuous observations of the solar wind and early warnings of approaching disturbances. The stereo spacecraft view the Sun from different angles, allowing coronal mass ejections to be tracked in 3 dimensions. Closer to the Sun, Parker Solar Probe and Solar Orbiter sample the solar atmosphere and wind at unprecedented proximity. Each mission adds pieces to the puzzle of space weather forecasting. Space weather is a global concern, and international cooperation has become essential. Agencies such as NOAA in the United States, ESA in Europe, JAXA in Japan, and ROSCOSMOS in Russia share data and coordinate forecasts. The United Nations Committee on the Peaceful Uses of Outer Space promotes collaborative efforts through initiatives like the International Space Weather Initiative. Policy frameworks encourage open data, joint missions, and shared research infrastructure. These alliances help ensure that the benefits of space weather research and mitigation are accessible worldwide. The future of space weather science will extend beyond our own planet. Researchers are beginning to consider how stellar activity affects exoplanets, influencing habitability and atmospheric evolution. On Earth, integrating space weather considerations into climate models may reveal subtle couplings between solar variability and long-term trends. Advances in materials, engineering, and distributed systems will allow infrastructure to tolerate and recover from space weather disruptions. As our society becomes ever more dependent on space-based technology, adapting to the cosmic environment will be a defining challenge and opportunity. Within the magnetosphere, waves and resonances play a vital role in transporting energy and particles. Ultra-low frequency waves can oscillate the entire magnetic field, pumping energy into the ring current and radiation belts. Whistler mode waves and chorus can accelerate electrons to relativistic energies or scatter them into the atmosphere. These wave-particle interactions reveal the plasma physics underlying space weather and are areas of active research. Throughout history, human cultures have told stories about the aurora. Indigenous peoples of the Arctic region saw the lights as spirits of ancestors dancing across the sky, or as celestial animals. In medieval Europe, red auroras were sometimes interpreted as omens of war or divine anger. The diversity of these narratives underscores how auroras have captivated human imagination across cultures and eras. Today, science explains the physics, but the sense of wonder remains. The sun's activity varies on an approximately 11-year cycle, moving from quiet periods to times of intense sunspot and flare activity. Some climatological records show subtle correlations between solar cycles and regional weather patterns, though solar variability is not the primary driver of recent climate change. Researchers continue to explore how ultraviolet radiation, cosmic rays, and solar magnetic fields may influence atmospheric circulation and cloud formation. Understanding these connections helps integrate space weather into broader Earth system science. Modern space weather forecasting leverages diverse modeling frameworks. Physics-based models simulate magnetohydrodynamic flows, particle kinetics, and ionospheric electrodynamics. Machine learning algorithms analyze historical data to identify patterns and improve predictions of storm onset and severity. Coupling models of the Sun, heliosphere, magnetosphere, and atmosphere requires interdisciplinary collaboration. Progress in this integration will enhance our ability to anticipate space weather impacts and mitigate risks. Commercial aviation routes sometimes pass near the poles to shorten travel time between continents. At high latitudes, the atmosphere is thinner, and the magnetic field lines funnel energetic particles toward the atmosphere, increasing radiation exposure and radio blackout risk. During severe solar storms, airlines reroute polar flights to lower latitudes to avoid communication loss and to reduce radiation doses to passengers and crew. These operational adjustments illustrate how space weather can ripple into schedules, fuel consumption, and passenger experience. The psychological impact of space weather and auroras touches on our sense of place in the cosmos. Witnessing an aurora can evoke feelings of awe and a sense of connection with the universe. In contrast, news of impending solar storms can generate anxiety about potential disruptions to the technologies on which we depend. Balancing wonder with preparedness is part of the human response to living under a star that occasionally reminds us of its power. Education and communication help translate scientific understanding into informed public perception. As the sun released its tempestuous breath, particles raced outward through the silence of space. The storm we explored in the previous part now stretched into the vacuum, a river of charged plasma carrying fragments of the star's magnetic field. It was not a sudden torrent, but a continuous outflow, a solar wind that had been flowing for billions of years and that now bore the imprint of a recent eruption. Riding that wind were protons, electrons, and heavier ions, each journeying through an expanse so vast that distances between atoms were measured in kilometers, yet they raced onward at hundreds of kilometers per second. To imagine that journey, we must slow our thoughts and picture the emptiness between worlds. The particles leave the sun's corona, where temperatures reach millions of degrees, and then traverse 150 million kilometers to our planet. Their velocity means the trip takes days, yet in cosmic terms, it is a brief crossing. As they move, they continue to stretch the sun's magnetic field into interplanetary space, creating a spiral pattern known as the Parker spiral that wraps around the solar system. This highway is shaped by the sun's rotation and the modulating effect of solar flares and coronal mass ejections, and its traffic never ceases. Along this invisible road, the density of plasma thins with distance, yet there is always a flow, a whisper of the star's breath across the darkness. The steady stream can be gentle, but when a flare or coronal mass ejection erupts, the number of particles and the strength of the magnetic field carried with them increase dramatically. These storms are like shock waves that sweep through the heliosphere, compressing and accelerating the ambient wind. They carry energy that can disturb the entire magnetic environment of a planet, and the speed at which they move means there is little time for Earth to prepare once the eruption occurs. Even in quiet times, the solar wind is far from uniform. It carries clumps of particles, streams of different speeds, and turbulent waves. The high-speed wind from coronal holes outruns the slower wind that emerges elsewhere, creating boundary layers where particles interact and generate magnetic turbulence. Solar rotation means these streams sweep past Earth in a recurring rhythm, giving our planet regular space weather patterns. The balance of slow and fast winds influences how energy is transferred to the magnetosphere, and when a storm arrives, this balance is disrupted, leading to sudden surges of energy. From the perspective of a charged particle, the path to Earth is guided by electromagnetic forces. These particles follow the magnetic field lines carried by the wind and respond to electric fields set up by the interaction of solar and planetary magnetic fields. Some accelerate and spiral, others drift, but all remain bound to the invisible architecture of magnetism. When a coronal mass ejection drives a shock ahead of it, particles can be accelerated to relativistic speeds, becoming cosmic rays that outrun the bulk flow. These high-energy particles are of special concern to astronauts and satellites because they can penetrate shielding and damage electronics. Eventually, the solar wind encounters the region of space where Earth's influence dominates. Before it reaches our planet, it passes through the orbits of Mercury and Venus, each of which has its own interaction with the wind. By the time the storm front nears Earth, it has spread out over millions of kilometers, yet its leading edge can still be sharp. The first sign of its arrival at Earth is a change in the flow of particles detected by satellites located at the first Lagrange point, a gravitational equilibrium between Earth and Sun. Instruments there provide us with an hour or so of warning before the storm envelops our magnetosphere. As the solar wind flows outward, it carries with it fluctuations in the sun's magnetic field that swirl and twist like currents in a river. These embedded magnetic structures are critical in determining the effect of a storm when it reaches Earth. If the field points southward, relative to Earth's northward field, the two can reconnect, allowing energy and particles to enter our magnetosphere. A northward orientation means the fields resist connection and the storm's impact is less severe. Forecasting the orientation of these fields is one of the great challenges of space weather prediction. The dynamic between the solar wind and the space it traverses gives rise to structures such as heliospheric current sheets and corrotating interaction regions. These features can persist for months and serve as pathways that guide energetic particles. When a storm passes through them, its effect can be amplified or diminished, depending on the local conditions. Understanding these structures requires a fleet of spacecraft positioned at different heliocentric distances and longitudes, a fleet that humanity has begun to deploy in recent decades to better understand and forecast space weather. Traveling along the solar wind highway, our storm eventually confronts Earth's magnetic domain. The region dominated by the planet's magnetic field is called the magnetosphere, an invisible shield generated by the molten iron in Earth's core. This magnetosphere protects our atmosphere from being eroded by the relentless wind. Its day side is compressed by the force of the incoming wind, while the night side is drawn out into a long tail that extends far beyond the moon. Within this cavity, complex currents and plasma populations circulate, forming belts of high-energy particles and a dense plasmasphere. Earth's magnetosphere is not a static shell, but a dynamic, breathing entity. As the solar wind presses against it, the boundary known as the magnetopause can move inward or outward. During strong storms, it is pushed so close to Earth that geosynchronous satellites find themselves temporarily outside the magnetosphere and exposed directly to the solar wind. On the night side, the magnetotail stores energy until it is released in explosive bursts that drive particles back toward the planet. These substorms are like miniature versions of the larger geomagnetic storm, injecting energy into Earth's near-space environment. At the heart of this shield lies Earth's dipole field, which is generated by convection in the liquid outer core. This geodynamo has sustained the magnetosphere for billions of years, offering life on Earth protection from solar and cosmic radiation. Without it, the solar wind would gradually strip away the atmosphere, as has likely happened to Mars and Venus. The strength of the field fluctuates on geological timescales, and on shorter timescales, it is constantly perturbed by currents flowing in the ionosphere and magnetosphere. The interplay between these currents and the solar wind gives rise to the phenomena we call space weather. The magnetosphere acts as a barrier, but also as a conduit. When the solar wind's magnetic field reconnects with Earth's, plasma can flow along the connected field lines into the magnetotail and back toward the poles. This process, known as magnetic reconnection, is fundamental to transferring energy from the wind into our space environment. It fuels geomagnetic storms and powers auroras. Reconnection can occur on both the day side and night side, and its rate determines the intensity of a storm. The details of this process remain an active area of research. Within the magnetosphere, different populations of charged particles form distinct regions. Closest to Earth is the plasmasphere, a donut of cold, dense plasma that correlates with the planet. Further out are the Van Allen radiation belts, where high-energy electrons and protons are trapped by the magnetic field. These belts expand and contract in response to solar storms, sometimes injecting energetic particles into low Earth orbit, where they can damage satellites. Embedded within the belts are ring currents and tail currents that contribute to the overall geomagnetic activity and can modify Earth's surface magnetic field. The magnetosphere is also threaded by electric currents that close through the ionosphere and even through the Earth itself. These currents maintain the global circuit that links the space environment to the ground. During geomagnetic storms, the intensities of these currents increase, driving rapid fluctuations in the magnetic field that can induce currents in long conductors on the surface. The geometry of the magnetosphere and the conductivity of Earth's crust determine how strongly these induced currents flow in power grids and pipelines. Thus, the invisible dance of particles high above us has tangible consequences on the ground. When the solar wind compresses the dayside magnetosphere, energetic particles trapped in the magnetosphere are driven earthward. As they spiral along magnetic field lines, they can penetrate to altitudes of 100 kilometers, colliding with atoms and molecules in the upper atmosphere. In these collisions, the energy of the particles is transferred to atmospheric constituents, exciting them to higher energy states. When these atoms and molecules return to their ground states, they emit photons, creating the shimmering displays known as the aurora. Auroras paint the sky with curtains of light that can stretch for hundreds of kilometers. They form in oval shapes, centered on Earth's magnetic poles, and occur at altitudes between about 80 and 500 kilometers. The primary colors, green, red, and purple, correspond to emissions from oxygen and nitrogen at different altitudes. During geomagnetic storms, the auroral ovals expand toward the equator, allowing people at lower latitudes to witness these spectacles. The shapes vary from dancing arcs and rays to twisting forms, reflecting the dynamic processes in the magnetosphere and ionosphere. The electrons responsible for auroras are often accelerated in the magnetotail. They travel along magnetic field lines toward the poles and can gain energy through interactions with electromagnetic waves. When these energetic electrons reach the upper atmosphere, they collide with oxygen and nitrogen, producing the familiar luminescence. Protons can also contribute to auroral emissions, but their signature is faint and often masked by the brighter electron aurora. In some cases, waves in the magnetosphere can modulate the electron flux, leading to pulsating auroras that appear to blink in the sky. The beauty of auroras hides the turbulent processes that create them. Each shimmering curtain marks a pathway of energy flowing from space into our atmosphere. During intense storms, auroral activity can be so strong that it disrupts radio communications and even affects ground-based systems. The same energetic electrons that paint the sky can ionize the upper atmosphere, altering its conductivity and changing the conditions for radio propagation. Pilots and navigators have long noted that auroras coincide with communication difficulties, and the correlation is not coincidental. Auroral displays have inspired myths and stories across cultures. To northern peoples, they were spirits dancing or battle fires in the heavens. In reality, they are manifestations of physical processes that connect the sun, space, and Earth in a single electrical system. Understanding them requires knowledge of plasma physics, magnetohydrodynamics, and the complex coupling of Earth's magnetic field with the solar wind. Yet even with our scientific insight, watching an aurora still evokes wonder. The slow waves of light invite contemplation, reminding us of our connection to cosmic forces. The colors of the aurora reveal the composition of the atmosphere and the energy of the precipitating particles. Oxygen at lower altitudes emits green light, while at higher altitudes it emits a deep red. Nitrogen yields blue and purple hues. During powerful storms, rare pinks and whites can appear when the particles penetrate more deeply and excite multiple emission lines simultaneously. Photographers who venture into the cold nights of high latitudes capture these variations, adding to the allure of the auroral experience. Auroras are not confined to Earth. Jupiter and Saturn boast their own luminous ovals produced by interactions of their magnetospheres with the solar wind and with moons like Io. Studying auroras across the solar system helps us understand magnetospheric physics in different contexts. The comparative approach enriches our knowledge of planetary environments and highlights how unique Earth's situation is. Our magnetosphere, though weaker than Jupiter's, is perfectly balanced to protect life while allowing for stunning displays of space weather. Beyond the auroras, geomagnetic storms have less visually appealing consequences. When the magnetosphere is disturbed, currents induced in the ionosphere and the ground can interfere with technological systems. One of the earliest recorded effects of space weather was the anomalous current observed in telegraph lines during the 19th century. Operators noticed that some lines carried current, even when their power sources were disconnected, and in some cases, the induced currents were strong enough to cause fires. These events puzzled early engineers, but we now understand they were caused by the rapid fluctuations of Earth's magnetic field during geomagnetic storms. The electrical power grid is similarly threaded by natural magnetic flux. When the magnetosphere is disturbed, geomagnetically induced currents can flow through the long conductors that make up transmission lines. These quasi-direct currents saturate transformer cores, causing them to heat and distorting the alternating current waveform. Protective devices may trip erroneously, taking equipment offline and leading to voltage instability. In extreme cases, such as the 1989 Hydro-Quebec blackout, a geomagnetic storm can trigger a cascading failure that leaves millions without power. Power grids are not the only infrastructure vulnerable to space weather. Satellites orbiting Earth rely on precise orbits and stable communications that can be disrupted by geomagnetic storms. In low Earth orbit, increased solar and geomagnetic activity heats the upper atmosphere, causing it to expand and increase in density. This expansion increases drag on satellites, causing them to lose altitude more quickly. Operators must schedule more frequent reboost maneuvers to maintain orbit, and in severe cases, satellites may re-enter the atmosphere prematurely. The same expansion of the upper atmosphere can scatter and refract radio signals used for communication and navigation. High-frequency radio signals, used by aviators and mariners, rely on the ionosphere to reflect them over the horizon. During solar flares, X-rays can ionize the lower ionosphere, enhancing the D layer and absorbing these radio waves. This absorption leads to radio blackouts on the day side of Earth that last for minutes to hours. Energetic protons produced in radiation storms can similarly enhance the D layer near the poles, blocking high-latitude communications. Satellite communications operate at higher frequencies and generally pass through the ionosphere, but they are not immune to space weather. Signals traversing the ionosphere experience group delay and phase advance, and irregularities in the plasma core's scintillation, which is a rapid fluctuation in signal amplitude and phase. During severe storms, attenuation and scintillation can become so intense that satellite links are lost altogether. The effect is frequency dependent. Signals in the ultra-high and super-high frequency bands used by satellites are susceptible when the plasma structure along their path is highly variable. Engineers mitigate these effects through design, but nature occasionally overwhelms their defenses. Global navigation systems like GPS are also affected when the ionosphere is disturbed. GPS receivers calculate position by measuring the travel time of signals from multiple satellites, accounting for the delay caused by the ionosphere. They use models based on average ionospheric conditions to correct for this delay. But when a geomagnetic storm enhances the total electron content, these models become inaccurate. Single-frequency GPS systems that normally provide meter-level accuracy may err by tens of meters during a storm. Dual-frequency receivers can compensate by comparing delays at two frequencies, yet in extreme conditions, even they can lose lock on the satellite signal. In addition to storms, natural day-night variations create equatorial plasma bubbles that cause scintillation and degrade GPS signals. These bubbles are not driven by space weather, but are intrinsic to the ionosphere's response to solar heating and Earth's rotation. They are most pronounced after sunset, near the magnetic equator, and can cause receivers to temporarily lose track of satellites. Understanding these phenomena helps engineers design more robust navigation systems and informs users about the limitations of their tools. Beyond communication and navigation, radiation storms pose direct hazards to spacecraft. energetic particles can penetrate spacecraft shielding, causing single-event upsets in electronic systems and degrading solar panels. In human spaceflight, increased radiation exposure is a health concern for astronauts. Aircraft flying over the poles are also exposed to increased radiation during strong storms. Operators may reroute flights to lower latitudes to limit exposure. These measures reflect the broader challenge of living in a space environment that is influenced by the variable sun. On the ground, engineers and planners have taken steps to mitigate the impacts of geomagnetic storms. Power companies monitor space weather forecasts and adjust operations to reduce load on vulnerable transformers during expected disturbances. They install monitoring devices to detect geomagnetically induced currents and have contingency plans for disconnecting lines or reconfiguring networks. Satellite operators track indices of geomagnetic activity to anticipate drag and schedule orbital corrections. In aviation, dispatchers factor in space weather conditions when planning transpolar routes. The ability to take these precautions depends on the human response to space weather. Over the past several decades, scientists have developed networks of ground-based and spaceborne instruments to monitor the sun and its effects on Earth. Satellites like the Solar and Heliospheric Observatory, SOHO, the Advanced Composition Explorer, ACE, and the Deep Space Climate Observatory, DSCO-VR, provide real-time measurements of solar emissions and solar wind conditions. These observations feed into models that forecast geomagnetic storms and provide warnings hours to days in advance. Without them, our technology infrastructure would be at much greater risk. Forecasting space weather involves predicting both the occurrence of solar eruptions and their impact on Earth. Solar physicists use observations of sunspots and magnetic fields on the sun's surface to identify regions likely to produce flares and coronal mass ejections. When an eruption is observed, coronagraph images show the direction and speed of the ejected material, allowing scientists to estimate when it will reach Earth. Instruments at the Lagrange point measure the orientation and strength of the magnetic field embedded in the solar wind as it approaches. Combining these data gives forecasters the information needed to issue alerts. Government agencies, including the National Oceanic and Atmospheric Administration's Space Weather Prediction Center, issue alerts, watches, and warnings for space weather events. These bulletins specify expected levels of solar radiation, geomagnetic storms, and radio blackouts, allowing utilities, airlines, satellite operators, and the public to prepare. International collaborations share data and coordinate responses, reflecting the global nature of the threat. Space weather forecasting is still a developing science, but advances in observations and modeling have significantly improved the lead time and accuracy of predictions. Public awareness of space weather is growing as society becomes more dependent on technology. Schools incorporate lessons about the sun and geomagnetic storms into curricula, and museums host exhibits on auroras and solar science. Amateur astronomers monitor sunspot activity and share their observations online. When a strong aurora is forecast, people in mid-latitudes venture outside at night to watch the sky, connecting personally with the cosmic forces that affect our world. This engagement fosters a broader understanding of our place in the solar system. In research communities, the human response includes launching new missions to study the sun and heliosphere. Spacecraft, like Parker Solar Probe, journey close to the sun to measure the origins of the solar wind, while others like Solar Orbiter view the sun's poles for the first time. These missions aim to answer fundamental questions about how the solar wind is heated and accelerated, and how magnetic fields erupt from the sun. The data they gather will refine our ability to predict solar storms and understand their consequences. On Earth, networks of magnetometers measure fluctuations in the magnetic field, while radar systems monitor the ionosphere. The integration of data from these sources provides a comprehensive picture of the space environment and its coupling to the ground. Sophisticated models assimilate observations in real time, forecasting not only the arrival of storms, but their impacts on specific regions and systems. This is an emerging field akin to terrestrial weather forecasting a century ago, and it carries similar importance for public safety and economic stability. Human response also involves international policy and cooperation. The effects of a geomagnetic storm do not respect national boundaries. A blackout in one region can cascade through interconnected power grids elsewhere. Agreements on data sharing, standardized space weather scales, and coordinated response plans enhance resilience. Organizations such as the International Space Environment Service facilitate this collaboration, ensuring that warnings are disseminated globally and that best practices are shared among operators and governments. Individual people contribute by heeding warnings and adjusting behavior. Amateur radio operators monitor space weather bulletins to understand why signals fade or improve. Farmers who rely on GPS for precision agriculture pay attention to forecasts to plan critical operations. Airline passengers occasionally learn that a flight path has been altered to avoid increased radiation exposure. Each of these actions reflects the growing integration of space weather awareness into daily life. The narrative of our cosmic storm is thus not solely about the physics of plasmas and magnetic fields. It is also about how societies adapt to the whims of our star. The solar wind's charged particles, traveling across the void, ultimately intersect with human economies, safety, and culture. Our response, whether through science, engineering, or personal engagement, is part of an ongoing dialogue with the sun. It reminds us that we are participants in a larger system that extends far beyond our atmosphere.